Among these types of clusters, you get 5,000 or so planar graphs that index aspects of this nonlinear optimization problem. And it's found that if you can solve this nonlinear optimization problem, you can find a function f of b which has all of the properties you want. You could ask computers to try their best to solve this nonlinear optimization problem in a bunch of real variables, but computers aren't very good at that. He has the idea that what if he could linearize this? What if he could chop up the problem into a bunch of linear programs that if you solve those linear programs, it would also solve the nonlinear optimization, or at least solve it enough to be able to prove the conjecture. And so this ends up involving quite a lot of careful analysis of the geometry of this 3n-dimensional space of clusters. It involves cutting up the space into various simplices and adding variables for angles between things and between angles in spherical triangles. Quite a lot of careful Euclidean geometry in this high-dimensional Euclidean space to turn it into a bunch of linear programs. In fact, I believe the estimate was about 10,000 linear programs. But he ended up doing that and showing that that sufficed, and then had the computation verify a bunch of the combinatorics involved with those 5,000 planar graphs, and then also had the computers do those 10,000 linear programs to show that, yes, you could do this optimization and find this function f, which worked for all the other clusters of packings of spheres, and showed that they were less dense.
Hi everyone, welcome to the stream. I'm just watching Leo Lecture's new video. That's what you've been hearing. So this one, Leo published a video today, which is extremely awesome. It's an hour and 42 minutes of an overview of history of computation. So if you're interested in theoretical computer science, go check it out. Yep. Hi Leo. Yeah, excellent video. I'm just 15 minutes in. All right, so I'll watch the whole thing. And okay, anyway, let's get started with the main subject of this stream. So I decided to do a stream on perhaps a series, well, who knows, we'll see, on introduction to proof writing. Okay, so this really is a fascinating topic, even though there seems to be some misconception about what this subject is about. Okay, why do we need to write proofs? Oh no, we all know that math needs a lot of proof, but what is the real purpose of writing proofs? And why? And is this a stereotype? And is the stereotype that pure mathematicians write proofs and applied mathematicians do computation really true? So the answer to the first question is really rather simple. Doing mathematics is a communal activity, even though individual experience can often be very solitary. Like you're working on a problem, you have no one else to talk to. This is very common. But at the end of the day, you're still trying to communicate your discovery, like your findings, to others, and sometimes to yourself, because math is complicated, and if you don't communicate clearly, you end up confusing yourself, right? So, which nobody wants. So in this process, human beings discovered a way to clarify thoughts, and that's why proof writing is so important, not just for math majors. Abraham Lincoln famously studied Euclid's geometry and was reportedly mastered the first 6 books of it when he was a lawyer and later a congressman and then president. So it's an excellent way to train one's character and discipline, and not just reason and capability. The reason I said that is because, as we shall see, the language of mathematics is very unforgiving, because once you commit to a set of definitions, you are committed, right? So you have to stick to it. I mean, you can change your definition, but that means changes all of its implication. You can't just say, oh, I'm going to propose a definition, and if I deduce something I found uncomfortable, I'm just going to change the definition halfway, like so many casual speeches in the real world, right? So in mathematics, that's completely unallowed. Inconsistency destroys the entire structure. If you say something, you mean something, and this is why To this day, I find learning mathematics to be such a humbling experience. Okay, you have to constantly check your own ego. If you want to if you can't smooth talk over a result, and you have to be completely honest with yourself. And these are skills and characters that you can train, and that has impact and your influence over your entire life. So I see the procedure of learning how to read and write proofs as a character building exercise, and not just for mathematics. And coming back to the topic of pure and applied mathematics, so it is true that most of the time, like pure mathematicians spend a lot of effort, perhaps majority of the effort, searching for proofs. However, that's typically how math is communicated at the end. But in the process, there's going to be a lot of computations. Like, for example, Gauss spent a lot of his has extensive notebooks, private notebooks, on just a crazy amount of calculations. Even though he only published results that he deemed beyond criticism. So Gauss only he had a motto for himself called "few but ripe." So what you only see is this tip of the iceberg. So pure mathematicians spend a lot of time working on computations and using proofs as a check on their intuition. So that's another great purpose of proofs. Sometimes in mathematics, you discover a pattern that seems to be true, that is likely to be true, but it is impossible for you to do all the computations to check whether that conjecture is true. So we resort to proofs. As for applied mathematics, of course, in a lot of the output of the applied mathematics were algorithms, computations, codes, right, that sort of thing. But when it comes to devising those kind of algorithm, a lot of the work actually was doing proof, because sometimes it's you need to be fairly certain that it's not just fairly certain. I need to know a solution exists. For example, there's this famous problem, $1 million problem on the Navier-Stokes smoothness and existence smoothness problem, existence uniqueness and smoothness problem. So it's a problem in partial differential equation that comes from fluid mechanics. Nowadays, weather predictions and other activity come from simulating the solution of Navier-Stokes equation. However, it is still unclear whether this PD actually has a solution, and the practical significance is real. It's not just some academic exercise. Okay, there's a solution. We don't really know or can prove whether it exists or not. We can just simulate it and simulate our way to reality. No, it does not work like that, because the computer can only work on discretized problem. Discretized problem may have characteristics that aren't the same as a continuous model. A continuous model, if it doesn't have a solution, or it has a solution that is currently beyond our understanding, our numerical simulation may very well give us garbage. So this is why proof is also fundamental to applied mathematics. The thing is, if you learn how to read and write proofs, the entire area, the entire kingdom of mathematics is now open to you. You are now able to walk on your own. You no longer rely on someone else to translate the papers and literature in general to you. And what's more important is that you're able to tell whether an argument is sound or not. Right? We've seen this phrase called mathematical maturity a lot in, for example, prefaces of textbook. Sometimes you'll say the prerequisite of this book is calculus, linear algebra, and mathematical maturity. What does that mean? Right? What does that mean? Does that mean you have done a lot of calculations? Of course, it counts. But the most important part of mathematical maturity in my opinion, even though the concept is very vague, in my opinion, is the ability to tell whether an argument is a proof or it's a heuristic reasoning. Okay, or do you do you manage to find a proof or not, right? So there's no this gray area that, oh, I think I found the proof, but I need someone else to check it for me. Of course, peer review is a thing, but mathematical maturity is really about when you solve a proof, you know you got it. You know you got it. But and when you don't have the proof, and you know, okay, there's certain things, there are certain gaps in my reasoning, and you're able to locate it and work on it. Right? So this is really this is as important as a child learning how to walk on his or her own. So yeah, so I strongly recommend everyone, okay, just not everyone, not just a math major, to give proof writing a try. I know, I'm not sure in other countries and continent, but in North America at least, in school level, high school level, proof writing is not mandatory, or at least if they cover it, it's not mandatory. Okay, if they ever cover it, it's not mandatory. If for more specialized courses, they do introduce proofs such as in Euclidean geometry, but not for a cross discipline. Okay, and so what, for example, from where I live, which is Ontario, Canada, not children, but students in their last 2 years or so study advanced functions. These are like pre-calculus stuff, right? The kind of functions we learn a lot, we use a lot in calculus, trig functions, exponential, log, the kind of thing. They have a dedicated course for that for senior high school student. There's like derivations about the properties of these functions, so which kind of resembles the process of a proof, but it's not formally regarded as such. And sometimes there's confusion of when the derivation constitutes a proof and when it isn't. So today, without further ado, we're going to start learning proof writing from scratch. Okay, we're gonna writing proof learning from scratch. We're not just gonna show fancy proofs, okay, and let you marvel at it. Okay, so we're going to start at the very anatomy of the proof itself, starting from the language of mathematics. How do you approach proving a statement from the structure of its statement? So we're going to start from the very beginning. So literally there's no prerequisite whatsoever. Okay, I always say math is a testament for character and not so much for intelligence. Of course, intelligence helps, but it's a matter of sheer willpower, like in my view. So that's why I as you can probably, if you can't tell already, I admire the subject a lot, and I have this how should I say, almost reverence towards it, because it is through this process and sometimes painful experience of learning and relearning that we achieve mastery of our own intellect. So anyway, with that out of the way, why don't we take a look at where we're going with this series. So first of all, let me just I'm going to give the main textbook I'm going to use. Of course, this is just my choice of textbook, and there's going to be a lot of textbook on the market. There's a lot of textbook on the market that covers roughly the same material. I chose this because I'm just more used to it. Okay, because I actually taught / tutored proof writing from scratch using this book, and I will recommend other books which are free that has similar content. Okay, so this book is called The Tools of Mathematical Reasoning, and it covers things that we just show on the PowerPoint slides: language, logic, proof techniques, set and functions, basic number theory, equivalence relations, cardinality, and real numbers. Okay, and it is barely over 200 pages. So it's short book by mathematical textbook standard, and it covers, in my opinion, a decent amount of material for like a first year, one semester course, and I like it a lot. And so this one, and which I recommend. However, it is not free, but this one, called Book of Proof, a lot of you guys already know that, is also an excellent alternative. It is completely free. It is part of American Institute of Mathematics open textbook initiative. It's called Book of Proof. So I'll just copy the link and paste it in the chat for these two masterpieces. All right, so this is by Lakens. This is the text by Lakens. I'll type it in chat. Okay, what's going on? I change it to English. Book by Lakens. Okay, and this one is by Richard Hammock, Book of Proof. They're both excellent. It comes to content, Lakens' book covers a little bit more than this one and moves at a faster pace. Okay, so if you use this one as a textbook for a one semester course, I believe it's a little bit short. So, but for what it covers, is still excellent. It's still excellent, and it has solutions as well. Lakens' book does not contain solution, and she justified it in the preface, which I will read in a bit. Okay, so before we come back to the main topic, I'm just gonna give a brief guideline of how to write mathematics, because writing mathematics is really not that different from writing in real life. Okay, even though the language itself is highly specialized and it has own idiosyncrasy, but the purpose of proof writing, as I mentioned earlier, is really just communication. It's really just communication, no more and no less than that. Okay, we don't write proofs to sound impressive. We don't write proofs to be pretentious and to gatekeep and make ourselves look smart. That's not the point. Writing mathematics has the same exact purpose as other forms of communication, like sending a text message to somebody else. You're trying to make a point. You're trying to clarify your thoughts, that kind of thing. And so when it comes to mathematical writing, okay, guideline for writing in general, and not just proof. Let's say, if you're writing a recipe, okay, if you're writing a recipe of your favorite dish, of your favorite homemade dish, follow the same advice. It will pay off. So, 1, write in complete sentences. Complete, grammatically correct sentences. Of course, in mathematics, we have shortcuts. For that, we use notations and other things. However, equations, notations should be embedded. It should flow with normal sentences. Complete, correct sentences. Grammatically correct sentences. It will save you a ton. Okay, a lot of people have this sort of say annoyance about PowerPoint, which I agree, because PowerPoints often don't contain complete sentences, and sometimes that creates confusion. So, which is one of the reasons I prefer textbook lecture notes over slides as well. So this gives you the opportunity to write complete sentences, and in the process of writing complete sentences, it is less likely for you to hide your own logical gaps, which will exist as you learn proofs. This is completely normal, and writing complete sentences will help you spot those things. All right, 2, which is also very helpful. 2, you begin with a relevant hypothesis. Begin with a relevant hypothesis. So it's like in a recipe book. You start with ingredients. What are you going to use, right? Instead of saying, just say, okay, turn the oven to 450 degree, and then you put the flour in the mixing bowl, add the cinnamon and whatnot. This is not good ordering, right? So first, state the relevant hypothesis. It's like putting the ingredients out, at the beginning of a recipe. So begin with hypothesis. So sometimes you will find, wow, this is kind of tedious, isn't it? Which brings us to the right amount of length and, how should I say, level of detail. Okay, at a certain point, we all start to omit certain details. Okay, for example, when you do a computation and you always use certain algebraic laws like associativity, distributivity, and all that kind of thing. When you first learn this stuff, it is often needed to justify the steps, okay, which law you just used. And after you reach a certain proficiency, you start just writing those deductions without the extra justification, right? And that's totally normal as well. It really depends on the subject matter, okay, the emphasis of what this result is about, okay, what's the proof, the intended audience, all kinds of things. So as I was saying, begin with hypothesis tends to be a fairly general advice, and it should not be omitted. Okay, beginning with hypothesis is something that we shouldn't omit. So, for example, I'm just going to give an example. We'll dive into this in a more systematic way. For example, let's see, we all know the product of two odd numbers is odd, right? This is not a terribly deep result. The product of two odd numbers is odd. So how do we begin with a proof for that? Right, so for example, you have a proposition that says the product, I'm using shortcuts, okay? Hopefully this is okay. The product of two odd integers. And actually one little caution about numbers, the word numbers. Okay, in modern mathematics, we don't typically say numbers on its own. You almost always specify what kind of numbers, because we don't have a unifying definition, at least in mainstream mathematics, of numbers. Okay, modern mathematics has largely given up on that project, defining a number. Instead, we have specific types of numbers: integers, rationals, reals, complex numbers, that sort of thing. The product of two odd integers is odd. So that's the proposition. So if we were to begin a proof for this proposition, we would begin with assuming the relevant hypothesis. Okay, so in the proposition itself, it contains no notation, no letters, okay, no symbols, that sort of stuff. It's purely verbal. So we begin by saying let m and n be integers. Okay, assume n and n are odd, and then do the deduction. Okay, this is a very simple example. Okay, and sometimes when you don't know how to actually write the full proof, you can make this kind of baby steps. Assuming the relevant hypothesis and write down what is needed. Okay, we'll come to that as well. And try to bridge the gap between the two. Because here, assuming m and n are odd, now you have something to work with. What's the definition of an odd number? Oh, and then you can say, by the definition of odd number, by the definition of odd integers, okay, by the definition of odd integers, there exists, and by the way, we'll introduce we will explain these kind of things that are called quantifiers. There exist integers. Sorry, right? There exist integers, say p and q, such that m equals 2p plus 1, n equals 2q plus 1. Right. So because you made the baby step and you know, oh, m and n are odd, so I should probably think about the meaning of those words. Right. So now you have two expressions to work with. So you can just compute the product m times n equals 2p plus 1, sorry, times 2q plus 1, and then you use the law of arithmetic for integers, basically to expand the product. Okay, so here, because we're not at the formal proof writing process yet, because today we're actually going to spend a lot of time talking about the language itself. So this is left as exercise for the reader. Okay, and then we're going to expand this, and you get 4pq plus 2p plus 2q plus 1. And then you notice, oh, I can actually factor out the 2, use the distributive law, so 2 times 2pq plus p plus q plus 1. Oh, this looks like 2 times an integer plus 1, right? So now you can conclude, oh, this is, because it has the format of 2 times an integer plus 1, we know it is an odd integer. And finish up the theorem and finish up the proof and say, hence, the product of 2 odd integers is odd. Okay, so this is not a complete proof, but I'm just trying to hammer the importance of begin with hypothesis. Okay, and I was saying about the level of details. What is the level of detail? So the level of detail is a tricky thing. The level of detail is, of course, we all know. Sometimes, for example, if you read a dense textbook like The Principle of Mathematical Analysis by Walter Rudin, this is a famous example. Often there's a complaint about the level of details. Right? It is often criticized as being too dense, that kind of thing. So what is the level of detail here? The level of details should be tailored towards the intended audience. Okay? As I mentioned, writing proofs is not about making yourself look smart. Okay? Writing proofs is about, writing mathematics in general is about communication. It's about communication. I mean, the subject matter, of course, can be difficult, and often it is. Right? The level of detail should be tailored towards the intended audience. And a good, I think, as a rule of thumb, the intended audience should be set as someone who has the same background as you, not in terms of exactly the same course being taken, just the reasoning capacity. Okay, the same level of reasoning capacity, but may not know what area you're working on. Okay, what exactly the problem is about, but is able to follow logical progression, like what we're going to cover in the levels course. So I know this does not sound like a terribly accurate or detailed description, which in itself is a bit ironic because I'm talking about the level of details and I'm not giving enough detail. So in a nutshell, is saying do not assume the reader already know what you're talking about. Even the smartest, oh hi inventive, long time no see. So I was saying like it's the level of detail should be you should assume your reader have the same mathematical background as you, but do not know the problem you're working on. Right? And of course, do not know what kind of what notation you mean. So let's say if I delete this sentence up here, if I don't write let m and n be integer and simply say assuming m and n are odd, right? This is still, I guess, probably still intelligible, oh, n and m probably refers to integers. But this creates unnecessary potential confusion. Right? So whenever we use notation, we should define it. We should not assume the reader already know when m and m is dropped, you automatically mean they're integers. So level of detail is more about what not to do rather than what to do. So do not assume reader already know what you're doing. Okay, so I think this is perhaps a good advice for students who are taking a course, because we tend to look up towards our professors and our TAs, and we know, oh, you already know this stuff. You already know the proof. So at least that's how I thought when I was a student. So I'm writing the proof to a professor, which really is not the right mentality in retrospect. Even though the professor or TA are the one who grade your proof, your intended audience should be your fellow classmates or your future self. Let's say if you write a proof and you come back to it a week later, can you still recognize your own thought process? Right? So do not assume reader already knows what you're doing. Okay. Big no. Okay, so that's point number 3. Point number 4, mean what you write and write what you mean. There's no room for interpretation in mathematics. Nada. Okay, everything is interpreted literally. Mean what you write and write what you mean. There's no room for interpretation. Okay. So this comes back to mathematics as a mean to sharpen one's character I was talking about. It enforces this relentless honesty. You cannot smooth talk over a proof. Okay. And 5 has to do with notations and terminologies, accuracy of notation and terminologies. So this is a little bit controversial because oftentimes terminologies are not standardized. Of course, we try to do it as much as we can, but sometimes terminologies aren't standardized, and this creates confusion and controversy. Okay, so a huge part of the purpose of this series is to give the terminologies that is now currently accepted by mainstream mathematics. Of course, by mainstream mathematics, we don't diminish other smaller schools. Okay, we try not to I mean, it's impossible for me to cover those schools, unfortunately, because to gain an understanding of those schools, you first have to understand mainstream mathematics, because those schools rises out of a response towards mainstream mathematics. So it doesn't matter what you choose to follow. At the end of the day, mainstream mathematics is still must be mastered before moving on to other more, should I say, currently more niche schools of mathematics. Okay, and 6, reference. So when you progress, it's becoming increasingly unlikely for a proof to be completely self-contained. So references often involves quoting the definition and theorems. For example, in this little proof, schedule proof I did earlier, I quoted the definition of odd integers. And in the computation, without explicitly doing so, I quoted the properties of integers. So the property of integers can be seen as axioms or theorems. It really depends on how you treat number system. But these aren't definition. Okay, it's an axiom or a theorem, but not a definition. So quoting definition, axioms, results. So results is an umbrella term for everything that is deduced. Results is an umbrella term that includes theorem, corollaries, and lemma. These are the most common ones. An axiom is a statement that is assumed to be true and on which we do our deductions. So the entire edifice of mathematics can be summarized into one sentence. If such and such and such, then such and such and such. Axioms do not mean self-evident. Okay, personally, I call this an Euclidean baggage. So you probably know from Euclidean geometry, it also has axioms, and ancient scholars tend to treat axioms as self-evident. In modern mathematics, axiom no longer carry that connotation. Axiom can look highly non-trivial. It is just something that we assume to be true and based that on, so you choose that as a starting point of our deduction. And the axioms, the way you choose axiom is a subject on its own. It usually comes down to trial and errors, comes down to attempts of unifying different strands, different lines of thought, to be as brief as possible, but be as consequential as possible. So the choice of axioms is an active, the way pure mathematicians in particular, how they work, has a lot to do with choosing the right definition and axioms. And sometimes it comes with trade-offs. So if any of you guys were following the measure theory stream, which is, of course, very advanced, we're not going to discuss measure theory on this stream, it's because sometimes seemingly innocent-looking axioms that you wish are true are incompatible, which is really fascinating. So a lot of mathematical research has to do with choosing the right definition and axiom. These aren't God-given. Okay, definition and axioms aren't obvious. These are results of sometimes decades, if not hundreds of years of intellectual battle. It takes a lot of debate to settle on a widely accepted definition. However, in classes, because there's this time constraint, right? You can't spend time endlessly debating definitions. So what tends to happen is definition and axioms are given without motivation. And you spend the majority of the lecture time and also homework, exam preps, manipulating those definitions and deduce consequences, which really is not how research mathematics is about. Of course, those skills are still important, but really finding the right definition and axiom, formulation of a theory, is very much the most time-consuming part. It's similar to how applied mathematics spend a lot of time on modeling the physical world. Right? The math may work perfectly, but if it does not describe the physical reality, it's useless for applied mathematician. Right? Just like in pure math, if you choose your axioms, if they are internally contradictory, the system collapses. Anyway, so I was on a little bit of a digression. Basically, I was trying to emphasize the importance of coming to definition, axioms, and results. For one reason is to be accurate, and another reason is to be consistent. Right? I said earlier that mathematics enforce this relentless consistency. If you define something, you have to stick to that definition. And if you change that, it's okay to change that, but be prepared to accept other consequences. So that's 6. Make sure you do the references. 7, about scratch work. scratch work. So this is another general advice on how to write proofs, because when we write proofs, it's typically unlike how we, say, calculate an integral. So let's say when you calculate integral, you typically go from the first line and you just proceed linearly. The first step is a substitution, second step is integration by part, and whatnot, right? You do that in a linear fashion from the first line to the second line. Writing proofs is a lot like writing essays. It takes scratch work. Sometimes you need to explore the ideas, look at special cases, find if there's any pattern that you can generalize, that kind of stuff. Sometimes you start from the premise and try to reach the conclusion. However, sometimes there's only very little assumption that you can work with, and so instead you start from the conclusion. Of course, you cannot assume the conclusion from line 1 because it defeats the whole purpose of the proof. But instead, you investigate, you unpack the desired conclusion and see what exactly you need. So there's this backward interplay of exploration when you do proofs. This is extremely common. But when you write the proof itself, it has to follow a certain progression. For example, a very common progression is, like I highlighted earlier, you start by the assumption, as always, and then you use what you discovered in your scratch work and write it in a forward manner. So this way, a machine can verify the process. Almost like a machine can verify the process. So, but the downside for that is it sometimes can appear rather unmotivated. Like I mentioned the book by Walter Rudin on principle of mathematical analysis, right? So that's the book. A lot of criticism goes like this: let epsilon greater than 0, pick delta equals half epsilon, and then just verify the half delta has the property of what is required in the limit, for example. So for beginners, this looks completely insane. How do you know delta equals half epsilon from the get-go, right? This is because proof writing is not linear. It is very likely that the author of the proof discovered the right choice of delta on the scratch work, and then when it comes to actual formal proof writing, reorganize it into a flow of logic that goes from assumptions and to the conclusion. So scratch work is often an indispensable part of discovering a proof. However, when you actually display your actual proof, you should not include the scratch work. It's like when you prepare a dish, right? You always create some kind of waste, like eggshells and plastic bags and whatever, right? When you present the dish to the dinner table, you don't leave those things. You don't bring those things together, even though they're indispensable in the process of making a dish. So scratch work is important for discovery. So don't be afraid to look at special cases and even assuming the conclusion on the scratch work, because this is often important to lead to discovery. However, do not present it. Don't write it. The scratch work, because, as I mentioned, it does sometimes have the disadvantage of appearing rather unmotivated, right? You can talk a little bit about motivation shortly in the proof, but that's not strictly necessary. What is strictly necessary in the proof is its correctness. It is the fact that the proof is correct and can be verified. To improve readability, to improve readability, this is for pedagogical reason, you can add extra commentary. It's like how a novel can contain illustration, but illustration is not essential to the story. Important for discovery, do not include it, should not contain any scratch work, but do not present in the final proof. Okay, so yeah, and of course, to do that, you first need to able to distinguish what is a scratch work, and what is actual proof. Okay, and no cross-out section; those are unprofessional. Okay, anyway, 8 is finally you proofread, just like writing an essay and whatever. When you finish writing a proof, reread it, see how the logic flows. Okay, does this sound natural to you from the start? Okay, it's like writing a piece of poetry, and often great proofs are like poetry. It's a poetry of reasons. Anyway, so these are some rather general advice, and it's easy to state, of course, but it takes a lot of practice to master them. And nowadays, because of AI, you can actually get some kind of feedback. Okay, I know a lot of people are really repulsed by the idea of learning with an AI, and yes, AI can absolutely make mistake. But language model are trained on the actual writing. So when you say ask AI, so does this sound normal? From a linguistic point of view, you will get actually decent feedback. Of course, that I consider that to be a last resort, meaning if you're completely isolated and you cannot find human guidance, real world human guidance, then by all means use AI, but use it with great suspicion. Okay, I don't think so. I was just doing the stream yesterday, and I got stuck on a problem after a few attempts. So I asked AI. And so the question is like a proof or disproof question, true or false, basically. So I suspected it was false. I was trying to give a counterexample, but I couldn't. I tried to give a counterexample, and actually we'll talk about those two. How do you create a counterexample? That's what are some of the general ideas of how to create counterexample. But I couldn't. Okay, I on my own. So I asked AI, and AI actually told me, oh, the result is true. I was like, oh wow, I've been wasting my time trying to find a counterexample, right? If the result is true in general, then that means no counterexample can be found. AI said the theorem is true. Sorry, not the theorem, but the result, the question, the statement given the question is true. So I got really confused. However, later on, chat told me, oh, there's actually a very simple counterexample. This was when I was doing my measure series stream. So the moral of the story is, even though AI nowadays is quite advanced, it made headlines of how it disproved conjectures. But at the end of the day, you are responsible for what you produce, not the tool. Okay, you are responsible for what you produce, and AI, well, because it's not human, it bears no responsibility. Okay, so use AI and whatever technology carefully. Okay, so at the early stage, I would say but I don't mean to discourage use of AI. In the process of engaging with AI tools, you will gradually discover what is it good for and what is still isn't super good for. All right. So with that out of the way, let's start from the very beginning. And let's start with language first. Language and logic. Language is, of course, part of everyday life. We're talking about mathematical language here. And as we all see, the way you write proof and you search for proofs is largely based on how a statement is formulated. Okay, so let's start with a notion of a statement. What is a statement in a mathematical sense? Of course, like all scientific subjects, mathematics requires evidence to justify its claims, right? While lab sciences use experimental data to justify their claims, right? In mathematics, logical reasoning is the standard. Mathematics is concerned with statement about mathematical objects. Statement. Okay, so what is a statement? So we'll explain that. Such as, and by mathematical objects, of course, that's also a very wide umbrella term. You can think of it as you include your familiar notions of integers, functions, and that sort of thing. The language of mathematics must therefore be precise and unambiguous. It has its own vocabulary and grammar. Logical arguments called proofs are used to deduce statements from basic assumptions. So there's assertions and negation. Yes. Is any particular negations is part of logic. We'll do that very soon. For the okay, so hang on, just think. So yeah, statement. A statement or a proposition is a full sentence that can be assigned a truth value to it. And it has exactly one truth value also. A statement or proposition is a sentence, is a complete sentence, first of all. A sentence so sentence basically is, it at a minimum, it needs to have a subject and a verb. A sentence which has exactly one truth value. All right. So that's a statement or proposition. So let's look at an example. By the way, by truth value, we mean, i.e., it is either true or false. There's no middle ground here. But not both, okay? But not both or something else is. I believe a lot of my quizzes in the community tab are true and false questions, right? So yeah, it's interesting because initially somebody asked me, can you add another option? Say, I have no idea, which is now a staple of my quizzes. True or false, I have no idea, which is okay. Acknowledging ignorance is the first step towards knowledge, and it's completely normal. It happens to everybody. But sometimes it can be inconclusive. So when that happens, typically that means the statement is ill-posed. Perhaps there's assumptions that aren't clarified, right? So basically a trick question. Okay, I tend to avoid trick question on the channel. I apologize if some of the questions are confusing, but what I strive for is to use standard terminology. And sometimes, if space permitted, if I feel like it, I'll actually write the definition after the question, so to minimize confusion. Okay, I get roasted every now and then for not posing the question clearly. So, so thank you for being accurate. So let's look at some examples and non-examples. What is a statement and what is not a statement? Right? For example and non-examples. So let's consider 2 plus 3 equals 6. Is that a statement? Right? Yes, it is a statement. Of course, we know it is false, but still, well, it is false. So it means it has a truth value. So that's why it is considered a statement. Statement, yes or no? Let's put a table like this. Statement. And truth value, true or false. The statement, yes, it is a statement, but it's false. Okay. Second is interesting. Second one says the 10 to the 46 digits of pi in decimal expansion is 7. Is that a statement? Look at the meaning of a sentence, sorry, a statement. Yeah, it is a statement because theoretically, if you write down the 10 to the 46 digit of pi, you will be able to tell whether it is 7 or not. Because a digit can only be one of the numbers among 0, 1, 2, all the way to 9 in the decimal expansion. So you will know whether it is a 7. However, to this day, we don't have access to that. Okay, we don't have access to that. So currently unknown. Currently unknown, but it will have a truth value regardless. Unknown currently. Okay, so this is interesting. So even though it is a proposition, we don't necessarily know its true or false value. Like many conjectures in mathematics. Some of the conjectures are proven, some of them are disproven, but nevertheless they have a true and false value. All right. So of course this is an oversimplification. There are statements in mathematics that turn out to be quote-unquote undecidable, which is really bizarre. But that's beyond the scope of this introductory course on proofs. Okay, those are dedicated fields of study in the field of mathematical logic, which is fascinating. However, I'm not a logician, and I'm not qualified to discuss these things in detail. And frankly, they are too far from my own field. Okay. Anyway, so the third one, just to giving these hints as inspiration for future study, is a sentence that has been proven. Is a sentence that has been proven that it cannot be proven a statement. Okay, so this one is really interesting. A sentence that has been proven it cannot be proven a statement. Well, the unprovability itself is a statement, right? So think about, we're getting way ahead of ourselves. So think about the continuum hypothesis. And actually, at a certain point when we discuss cardinality, we will be able to state what continuum hypothesis says. So assuming the standard axioms in the set theory, the ZFC set theory, it has been shown that the continuum hypothesis cannot be proved or disproved. Right? That result itself is proven. Right? Is proven. So the unprovability under the ZFC framework is a statement. And so if then you say, okay, assuming ZFC is the continuum hypothesis a statement, right? So it doesn't seem to fit that definition, right? The continuum hypothesis is a statement which is proven to be undecidable. And quite frankly, I don't know. So, and for the vast majority of everyday mathematics, you aren't going to be dealing with those statements either. So we will leave the question to logician. As I said, I'm not a logician. All right. Third, every prime is odd. Every prime number is odd. Is that a statement? Yeah, it is a statement. Because there are ways to assign truth and false value. Right? Let's say if you find a prime number that is not odd, then the statement is false. Otherwise, it's true. So it is a statement. But of course, we know it's false because of 2. 2 is a prime number. Prime number will be defined. So 2 is a prime number, but 2 is not odd. So that's a counterexample. To disprove a statement typically amounts to finding a counterexample. Okay. Okay. So as I was saying, this is a proposition and statement. I forgot to add one thing: notations. Notations for proposition are typically single letters. I like to use capital letters. Big P, big Q. Usually start with big P. Okay, big P, big Q, R, etc., etc. However, in computer science, there seems to be another convention that uses lowercase letters. So computer scientists like to write little p, little q, little r as for propositions. But we're going to use big letters, okay, just to state that here. We use big P, big Q, and big R for their for proposition. So we're going to be dealing with abstract proposition, right? Ignoring the actual content of the statement, but simply concentrate on its truth values. Oh, Leo, it's important part of the proof is finishing like QED. Oh, fuck. Yeah. It's such a, you know what? It's such a satisfying thing when you write this at the end. It's such a satisfying thing when you draw a little tombstone at the end of the proof or write QED. Yeah, it's super satisfying. Those like TikTok videos of a satisfying moment or something like that. I was like, man, the moment you finish a proof and you draw that little square at the end of the proof is the most satisfying thing ever. Fourth, what is 2 plus 3? Or that third option. Oh yeah, and that third option for sure. Yeah. 2 plus 3. Okay, so what's 2 plus? Is that a statement? What is the problem here? What is the problem here? There is no. First of all, 2 plus 3 is not even a full sentence. It's like, if you say 2 plus 3 in real life, that's imperative, right? It's like telling someone to add 2 and 3. So if it's an imperative, then it's not a statement. So imperative only consists of a verb. Go here, do that. So this is not a statement. So the truth value is meaningless. There's no truth value to that. You can say, okay, 2 plus 3 equals 5, like this, or 2 plus 3 equals 6, which is false. But nevertheless, that's a full sentence. 2 plus 3 equals 6. Well, actually, you know what? A fun caveat. Before I started YouTube, I always say 2 plus 3 is equal to 6. But later on, I got corrected in chat and say, not chat, but comment, and say, you just say equals something, not is equal to something. I figured, oh, you know what? Equals is shorter anyway. So I'm now switching to equals. After over 30 years of, over 30, I didn't learn English when I was born, but certainly decades of experience. So right now I'm switching to equals. This is undefined, NA, okay, not applicable. 5, so got 5. So m plus 1 greater than 3, is that a statement? Is this a statement, chat? M plus 3 greater than 3. You see, this is a complete sentence. If you translate the mathematical notation into English, or whichever language you prefer, this is a complete sentence. It says n plus 1 is greater than 3. That's a full sentence. However, it is not a statement because it is impossible to decide whether this is true. The truth value of it depends on this variable n. So it is not a statement. The truth value is not applicable. However, if you specify the value of n, of course, then you can decide whether it is true or not. Or, as we shall see later on, another way to assign truth value to this sort of thing is to add quantifiers. Say, there exists an n in the set of integers such that n plus 1 is greater than 3. Or you can say, for all n in the set of reals, n plus 1 is greater than 3. Okay, those things are called quantifiers, which we'll cover shortly. But this thing on its own, okay, this thing on its own is not a statement, but is often called a predicate. It's called a predicate. And n is the so-called free variable. Okay. So in itself is not a statement. Okay. Anyway, and now we understand what a statement is. We can combine different statements into more complex statements, which brings us to the notion of logical connectives or operators. Computer scientists like to use the notion of operator, use the word operator. But here we're going to just say connectives. So the idea of connectives is really already familiar in everyday English. Say, the sun rises from the east, and the sun falls in the west, right? So you can connect different statements into more complex propositions. So really, the huge edifice of mathematical, just mathematics in general, is built upon connecting simple propositions into this massive network of results. Okay, so this might seem like a boring exercise to define connectives, but this is the building block of the, along with propositions and quantifiers, are the building blocks of modern mathematics. So we're literally describing the bricks and mortars of mathematics. So connectives. And it is here we can already see some rather interesting phenomena, connectives, and what it means to say, what are the purposes of mathematical definitions, really, connectives. Okay, so there are a few connectives, and we're going to see them one by one. So first one is negation. It's the easiest one. So negation is defined, it uses this weird symbol here. Okay, it looks like a L that's fallen down. Okay, whenever I see this, I always think of this little tool from IKEA furniture. So when you buy a package of IKEA furniture, it comes with various parts and also a little plastic bag with screws and stuff. And in there, there's this L-shaped tool, like a screw. And every time I see that, I think of, oh, that's the negation sign. So P and negation of P always have opposite truth value. So P, if P is true, then negation of P would be false. If P is false, then the negation of P would be true. Right? Sounds completely natural and unambiguous. Right? Okay. So here you can already see an example. It's called Allen's wrench. Okay. I didn't know. Yeah, / negate. This is a LaTeX code for that. And actually, sorry, my bad. Some people ask me, why don't you do LaTeX on live? Well, the first explanation is I'm very slow with that.
If you come to my Discord server, and I sometimes type in LaTeX over there, because in Discord server there's a bot that converts LaTeX to LaTeX code to LaTeX, and I often make mistakes there. That's the most important reason, to hide my own incompetence. And the second is to minimize distraction, because LaTeX code takes rendering. LaTeX code takes rendering. Let's say if you type something like \negate on screen, right, it takes some rendering for it to convert into this. I think it introduces, in my opinion, okay, it introduces extra friction. So if somebody just wanted to concentrate on this logical operator, they have to do this mental conversion. This is a LaTeX code for that. So I try to minimize those things. And with this, with this negation connective, we can see. By the way, this is a definition. Okay, this is a definition of negation. Definition of negation, and using this definition, we can already deduce a consequence called the double negation result. Okay, the double negation, sometimes called the law of excluded middle. But once again, I'm not a logician. Perhaps my phrasing is not completely correct. But let's just stick to double negation. Let's not invoke the excluded middle here. Double negation. So double negation says the following. It says P and the double negation of P are logically equivalent. So I'm going to use this symbol. To represent logical equivalence. We'll give a more formal definition later, but here we're just going to state what this means in this particular case. So here you have P and you negate P. And we have double negation of P. So we're going to put everything in the truth table and compare their truth values. So unless you learn and practice a given modality, it is indeed an extra translation layer for the brain. Yeah, this is, I think, what I was trying to get to. So yeah, so basically here, P negation of P, and double negation of P would be just true. Okay, sorry. Yeah, true, false, true, the first row. And the second row would be false, true, false. And what we can see is, in all rows, in all instances, P and double negation of P have the same truth value. They always agree. So this is what we mean by logical equivalence. And we'll give a formal statement, a formal definition for that. Okay, what do we mean by saying two propositions or two statements being logically equivalent? What is interesting is that even though this law, double negation equals the statement itself, logically equivalent to the statement itself, is widely accepted in, modern mathematics, there are schools of thought that rejects this, which sounds like insanity, right? What about the triple negation? Well, it just gives you back to negation, no? Because this is, you can think of it as a quote-unquote idempotent operator, or sorry, not idempotent, but involution. Is that the right word? I'm not an algebraist, okay? Really just equivalent to minus n. Kind of. Double negative equals, actually, I would think that's actually highly non-trivial. I mean, perhaps not highly non-trivial, but double negative removes the negative sign, equals the plus sign, is later we'll see a consequence of the field axioms. The field axioms in algebra. And perhaps it also works beyond field, I believe. But you can actually prove double minus is positive from the field axiom. I think the most constructive interested people have a wrong interpretation of the rejection. Yeah, actually, I don't really understand it. I'm just trying to raise awareness that not everybody accepts this. I think the intuitionists accept, say say this. Intuitionists would accept P implies the double negation of P, but not the other way around, right? So this has massive consequences. So let's say if you assume minus P, not minus, but the negation of P, and then you see that, oh, the negation of P is actually false, you can't just say P is true, right? So which is a problem because in mathematics, proof by contradiction is a powerful tool. So if you cannot get from double negation to the statement itself, you cannot use proof by contradiction. But Leo says in theoretical computer science, we domain expand from F2 to larger, usually finite fields called arithmetization. Okay, interesting. Yeah, as I was saying, like here, even though this sounds completely obvious to us, there are schools of mathematics for philosophical reasons that rejects this, or at least partially rejects this. And over there, you cannot do proof by contradictions freely, which sounds like a nightmare to me. So I don't know. Please, if you know more than I do, which probably very likely to happen, please let me know. Like as I said, I was just giving out my own understanding. As far as I understand, the intuitionist would acknowledge P implies double negation of P, but not the other way around. Okay, so, if you're interested, go look it up yourself. Okay, and share it in the comment or Discord or whatever. I would love to hear about it, because I'm not a logician, as I said. So the next connective would be so-called conjunction or AND. Conjunction. Conjunction has this symbol. It looks like a big lambda. It's like an A with the middle dash removed. So that's the symbol. It's basically a wedge. Conjunction or AND. The AND operator or AND connective. Computer scientists tend to use the word operator. So definition. So imagine, of course, when you say AND, you're connecting two propositions like P and Q. So it's defined as follows. P and Q is true if and only if both P and Q are true. Once again, this is completely intuitive. So in the truth table, we should have four options. True, 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 false, false, true, false, false. And by the way, a lot of my quizzes have that format because sometimes I wish to emphasize the contrast of two similar looking results. So I do two true and false questions at once. And the options all look like this. And because of YouTube quiz format, you can only have four options. There's no option for, oh, I don't know the answer. Even though I wish I could add that. So seems like a perfectly made format for this type of question. True, true, false. Okay, which can be interesting in my opinion, because sometimes there are subtle differences between similar looking statement, or say a statement and its converse, which we'll come to. Okay, one implication is true and one implication is false. Pretty interesting. So as I was saying, only the first row where you have P and Q both true, that the AND operator returns a true. Every other scenario, oh sorry, what I was doing. So here the last two should be false. Okay, everything should be false. Should be false. So in computer science, sometimes you encode true as 1 and false as 0. So the AND operator now has a nice correspondence with multiplication in algebra. So if you write, say, true is 1 and false is 0, the result of the AND operator is just a multiplication of the two truth value. It only equals 1 when both values are 1. And also, this is useful in probability and statistics. In statistics, probability and statistics, we often handle events, and events occurs or not, right? Is 1, 0 always 0? Yeah. You mean 1 and 0? Yeah. If you have 1 true and 1 false,
then true and false is false. This is always, I don't think there's any controversy surrounding that because it's such an intuitive definition. Right? So yeah, so this is, and as I was saying, in probability and statistics, often we work with events, whether event happens or not. Right? So when you deal with those sort of situations, often we do is to define so-called indicators for those events. An event, say A, would have an indicator function of A with a with a subscript A. Subscript A. So this is the indicator. It equals 1 if A occurs. If A occurs. Okay, then it's 0 if A does not occur. Does not occur. Okay. And it's hugely convenient for handling joint events. Because if you have a sequence of events, A1 all the way to AN, to encode the joint event, you just multiply their indicators. Right. So this is a nice little extra information. Okay, conjunction. So this one should be pretty intuitive. The next one needs a little bit of a care. So it's called or disjunction. This one needs a little bit of a care because in English, often or is ambiguous. So or first of all, it is denoted as the upside down wedge. It's exactly the conjunction symbol flipped upside down. All right. So the definition of or is as follows, and we'll contrast that with the usual way we say or in English, which can be sometimes conform to the mathematical definition, sometimes don't. Say P and Q. P or Q. Say the headers are exactly the same. True, 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 false, false, true, false, false. Okay, these are all the possibilities. The P or Q is true if at least one of the propositions P or Q is true. So true, true gives true, true, false gives true, false, true gives true, and false, false gives false. So only in the last scenario where you have false. Right. So anyway, so this is what we call an inclusive OR. So by default, OR in mathematics means inclusive OR. In real life, however, we don't always mean inclusive OR. Let's say, imagine if you go to a restaurant. I don't know, like McDonald's, and the waiter asks you, do you want French fries or onion rings as your side? Do McDonald's still offer onion rings? I'm not sure. Burger King does. So what they mean is actually exclusive, right? If you get, for the same price, you can only get French fries or onion rings, but not both. Right? We're not exclusionary in mathematics. Well, if we really want to, we can be, right? There's this XOR operator. If we want to mention that, oh, we are exclusionary, then we will say so. Okay? Otherwise, we are inclusive. So how nice we are. How nice are we, right? So this is, yeah, I know one of the most common gates that come up in nature is and not, A and not B. Interesting. What do we mean by gate that comes up in nature? Right. This has a lot to do with the circuitry stuff, the gate, logical gate, the complete operation. It's a complete operation in the sense that all the operators can be defined in terms of it, right? A and not B. You can define other things like implications or whatever using that and not. Is that right? I think I've seen that. Okay. Anyway, this is a bit more advanced than we were discussing, but thank you very much, Leo, for mentioning that. So there's actually a dedicated study in mathematical logic on
say, what would be the most fundamental logical connectives? So yeah, okay, I think I got it. So this is the OR operator, and sometimes in real life, OR means inclusive OR. Say, a professor of topology say, oh, you can take this course if you have completed a previous course on analysis or abstract algebra. Of course, if you have taken both, then fantastic. Right? More mathematical maturity, I guess. Right? But in those situations, we mean inclusive OR. So in mathematics, by default, we mean exclusive OR. So far, this is still rather intuitive. Okay, so that's disjunction. And from this definition, we can have more logical equivalence, actually. Here we have a theorem called the De Morgan's law. De Morgan's law, because, guys, if you know more about this, please let me know about the origin of this naming, De Morgan's law. When I first learned about this, I was kind of surprised that somebody's name is attached to this, because it sounds super obvious. It's like P and Q take a negation is equivalent to the negation of P or the negation of Q. I was like, did De Morgan really discover this, or he just the guy who formulated this? But because surely people before him knows about this. And by the way, De Morgan was a contemporary of Stokes. The Stokes theorem. As if you've seen some vector calculus, Stokes. So he was a figure in the 19th century. But surely people before him knows about this, and they just didn't have a name for this law. Because I was confused. I didn't know about how it was named after him. Anyway, so the other version, which is symmetric, looks like this. So the negation of P or Q is equivalent to the negation of P and the negation of Q. So it's like if you want to pull the negation sign into the bracket, you have to swap OR to and from AND to OR. Okay. Once again, the intuition is very clear. Let's say if you P means student A has taken real analysis. Q stands for student A has taken abstract algebra. Then the negation would be, and the end would be, okay, the student has taken both subjects. The negation for that would be he either hasn't taken real analysis or he either has not taken abstract algebra. Like for me, for example, I've taken real analysis, but I've never taken abstract algebra formally. So I fall in that category. Okay. So next, if you have P or Q, right, P or Q, to negate P or Q, then P and Q both must be false. Please teach numbers here. Actually, later on, it has, not today, but I hope I can continue this series, but we will see some basic numbers theory. Congruence mostly. And real analysis also, yeah. It will come to the end, because right now we're dealing with fundamentals of proof writing. Those subjects have their own intrinsic difficulties. We don't want the difficulty of proof writing itself to compound with the difficulty in the subject matter. So that's why we're spending time on the fundamentals before we proceed to the more advanced subject. I mean, if you're interested in real analysis, you can follow my measure theory stream, which is, I guess, it's more advanced than intro analysis, but we do cover like a review, actually sometimes in quite some detail about basic real analysis. For example, in the discussion of outer measure, we reviewed the notion of a compact set. And in yesterday's session, we reviewed the notion of a Cauchy sequence. So these are more like fundamental real analysis. If you're interested in real analysis, be sure to, don't be, there's no such thing as be sure, but I recommend you check out the measure series stream. And if you have questions, like, let me know. So anyway, so these are De Morgan's law, and the proof is once again, these are very, so to say, very special proofs, so to say. Typically, we don't see proof like this as we go along. The proof we see are typically like an essay, right? As we mentioned in our guideline. You state your assumptions, blah, 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 write in full sentences. So these are very like specialized proofs, right, for proving logical equivalences. So how do we prove De Morgan's law? We will prove one and leave the other as exercises. Leave the other one as exercise. So if you just write down the truth table, like we did in the previous proof, at the end of the proof, draw a little square here. So be sure to write down all the intermediate steps, if that makes sense, or the sub-formulas, as they call it in mathematical logic. So this is quote-unquote a formula, propositional formula, and if you strip away the negation, then P and Q is also a formula, that kind of thing. So I'm saying is you start from the atomic formulas, basically the prepositional variables themselves, P and Q, and then put sub-formulas in the other column. So P and Q would be having its own column, and the negation of that, the negation of P and Q. Okay, not P, not Q. We're dealing with the right-hand side here, and not P and not Q taking OR. Okay, as you can probably tell, let's say if the equivalence is complicated, if it contains many subformulas and many variables, and in particular the latter case, the latter. If you have many variables, proving logical equivalence using truth table can be extremely inefficient. Remember, here, because we have two prepositional variables, P and Q, it has 4 rows in total. True, 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 false, false, true, false, false. In general, if we have n prepositional variables, then the number of rows in the truth table would be 2 to the n. It grows exponentially. So it becomes extremely difficult to verify truth table. Right? So for that reason, mathematical logic has dedicated algorithm, like checking so-called quote-unquote satisfiability, and not just logical equivalence, but it's auto satisfiability. Satisfiability means a formula can ever be true if there is at least one true in these columns. So it's an important problem in logic called SAT, short for satisfiability, and there are many restricted versions of it. It's a fascinating field. Even from these simple-looking connective important problems and difficult problems can be posed. So P and Q, let's just repeat the truth table of AND, true, false, 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 going from up to bottom. Negation, just flip the truth value, you get false, true, true, true. Negation of P, so P is true, true, false, false. Negation of P would be false, false, true, true. Q is true, false, true, false. Negation for that would be false, true, false, true. And then finally taking OR. OR is true if at least one of the things taking OR is true. So we notice that the last 3 rows has at least one true, so they're all true. The first row is a false, false, so you just get false. And look at the 2 columns for the left-hand side and the right-hand side. So they correspond exactly, right? So this proves the first law. The first, De Morgan's law. And the second law can be proven similarly. Okay? So these are the definitions of and, conjunction, and disjunction. Okay, so, and now let's take a look at a, hang on a second. Yeah, let's take a look at the next connected, which is perhaps the most controversial, or not controversial, but most confusing for beginners. It's implication. And unfortunately, it is the most important connective. It is the most important connective because without it, mathematics would just be, would have no logical structure. Mathematics is all about if such and such and such, then such and such and such. So it's an implication. So now we're going to define the connective implication. The connective or implication, and this is where things gets a little bit perhaps unintuitive. And the symbol for that would be this symbol imply. Computer scientists sometimes just write a single arrow. Okay, but here we'll use the double arrow notation. Implication, and sometimes it's also called conditional statement. Conditional statement because it has a condition. If such and such and such, then such and such and such. All right. Here's the definition. PQ and P implies Q. Okay. And I think actually, shameless self-promotion, my first quote-unquote viral video was on this implication symbol. Well, by viral, I mean when I had like 100 subscribers and I got over 1,000 views. That was viral to me. Okay, so I made a video very early on in my YouTube career answering the question why the truth table of imply is defined as such. Okay, so here's the truth table. True, true implies true. True, false implies false. False, true implies true, and false, false implies true. So as you can see, the only scenario where P implies Q is false is the second one. If the hypothesis P is true and the conclusion Q is false. And of course, this raises a few questions. Right, so what about the last two rows? What is going on here? It says if P is false, then it doesn't matter what Q is, the implication is always true. And those two rows have a special name called vacuous truth. Is that how you spell it, with a W? My goodness. I can't even spell confidently. This is a vacuous truth. Vacuously true. So why is this defined this way? Because if you think about it, it is kind of awkward. It's like whenever the hypothesis is false, you can derive everything. You can derive everything. So isn't that a little bit unnatural? And also there is this misconception about what this P implies Q really means, right? So it's like, for example, if you put two random statements that are true, say the sun rises from the east, right, and something else, okay? And let's say today is August the 29th. And you put them together, this will give you a true statement according to this table, right? But if you translate that into natural language, it sounds like if the sun rises from the east, then today is the August of 29th, which sounds completely nonsensical. So what is really going on here? So first of all, I would like to mention this is quote-unquote formal logic. In ancient time, like logic was studied. Also, logic was already a field of study because I suspect it has to do with the debate culture in ancient Greece and Rome. Because there's a lot of debate, and sometimes you just get this empty rhetoric and the contest became a competition in demagoguery, not a pursuit of truth. So some sort of rule needs to be established to articulate, so to decide whether an argument is true or false. So for that, people devised a different scheme, and one common scheme is called formal fallacy. Sorry, to detect fallacy. One common category of fallacy is called formal fallacy. So formal fallacy and also informal fallacy. I suspect the invention of abstract logic is to handle formal fallacies. Formal fallacies. So let's say if a statement fails the formal fallacy test, then it has no validity whatsoever. However, if it conforms to the formal test, let's say if you check for formal fallacies and there aren't any, right? That's just a requirement for no other fallacy. So if it contains no formal fallacy, it does not automatically means the argument makes sense, right? Because there's still informal fallacies to look out for. So the formal logic serves as the first line of defense, so to say, of detecting fallacies. Right. So therefore, we emphasize that even though if you have two true statements, P and Q, even though the logical operator tells you P implies Q is true, it does not automatically means, okay, in the actual context, P implies Q is a valid deduction. It just means no formal fallacy. Okay, so that's the first thing. And what remains to explain is the notion of vacuous truth. This is where a lot of explanation, in my opinion, gets rather hand-wavy. So often you hear this kind of explanation for the vacuous truth. It's like saying, if you buy an insurance policy, okay? You buy an insurance policy and say if you get into an accident to no fault of your own, they will pay you X amount of dollar maximum, something like that, right? So let's say during the duration of the coverage of the insurance policy, everything is safe and sound, nothing happened. So the triggering event, say P, is always false. It never happened, right? But Q would be the reaction given by the insurance company. Pay you money or not. Let's say because nothing happened, right? So because nothing happened, so you will of course not get the money. But in this case, you cannot say the insurance contract is false. The insurance contract says if you get into accident with no fault of your own, then you will get paid with X amount of dollars. So there's no way to negate that piece of contract, and therefore we call it true. So that's the first analogy. But on that ground, it gets rather murky, because you can also say, well, because there's no evidence against, so because you said because there's no evidence against the policy, then you just call it true. But you can equally argue, say, well, there's no evidence for that either, right? So let's say, imagine the insurance company really is scummy. It's just lucky that you didn't get into trouble, because in reality, they are pretty scummy, and you got into the triggering event, so to say, and they would actually deny the coverage. But it's just that based on your experience, you have no way to detect that. So it gets really murky when you couple this with real world scenario, in my opinion. So it's a way to memorize the table, but rather than an explanation. The actual reason for defining the implication this way and not the other way is actually quite sophisticated. Okay, and we'll give an explanation. as we shall see later on, to do the proofs method that we want to, if you define implication in any other way, it will give you massive problem. Okay, so actually, what do we expect out of this implication? So what are the expected properties of this implication? Let's just write the desired property on the side. So first of all, we don't want P implies Q and Q implies P to be equivalent. We don't want that, because that's a common logical fallacy. Right? So it's like saying if a bird is how do I give an example? Let's say if you don't wear a seatbelt, while you drive and you were caught, you will get a ticket. Right? The converse for that would be you getting a ticket. But that doesn't automatically mean you didn't wear a seatbelt, because you might have violated other traffic laws. So we don't want P implies Q to be equivalent to Q implies P. Right? Actually, a lot of real-world logical fallacy comes from treating those two as equivalent. Do it with milk and eggs. How do you do that? Okay. Anyway, so we don't want that. We do want another thing. So you have this intuition about logical reasoning at first, and then you try to devise a definition of imply to formalize these. Okay, not to prove these, but these are just logical rules, inference rules that we accumulate from real-world experience, because otherwise you get chaos. Right? So we don't want P implies Q to be equivalent to Q implies P. You don't want that. And we do want P implies P to be equivalent to so-called contrapositive. That is, negative, the negation of Q implies the negation of P. So that's what it's saying. So, if it rains, then the ground would be wet. And the contrapositive for that would be, if the ground is dry, then it didn't rain. Okay, so that's the equivalence that we want. So actually here, because we only have finitely many options, first of all, let's just treat the two rows here, the first two rows as uncontroversial. The first two rows, I think we can safely accept those. Those are pretty intuitive. True, true implies true. True, false implies false. Provided if you don't equate formal soundness with actual soundness. Right. So yeah, those first two rows should be rather intuitive. But because here you only have finitely many options, you can actually test your options. So imagine you have currently this situation. Let's say, imagine putting yourself in the shoes of the inventor of formal logic, of truth table, and say, okay, so I want to decide what do I do with the last two rows. What are the options you have? Well, one option is to simply leave them undefined. That's certainly an option. It's like in algebra, you don't have to define division for every pair of numbers, a over b. You can just say, okay, a over 0 is undefined. You can do that. So it can be an option to say, because of the triggering event P never happens for the last two situations, we simply refuse to give a value of P implies Q. So it's just undefined. That's your first option. Say false, true, false, false. Those two, you're going to leave them as undefined. Say this is options. Options for the definition. You can leave them undefined, simply put a question mark here. You actually, not question mark, but undefined. Say UD, undefined. All right. Okay. Anyway, so that's the first option. So you can actually test out whether the two desired goals holds true. Okay, so I mean, you can say this is your definition. Okay, so suppose this is our definition, and there's certainly a intuitive case to be made about that, right? The triggering event did not happen. We have no ground to decide whether the implication is true or not. So we just leave them undefined. But if you accept that as your definition, you have to run against your desired proposition, because we don't define these things for fun, do we? At least most of them don't. We're trying to formalize logic and decide what inference, or not inference, what deduction rule is valid and what isn't. So you can actually check these definitions. So this is the first one. And how many other options do we have? Well, the only thing that needs to be specified are these two options here. So there are four options: true, 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 false, false, true, false, false. That's it. So you got finitely many options. Okay, and in fact, this will be a fun homework. Go check these out. So anyway, I'm just gonna copy the table and change the definitions. Okay, so the second option is the actual option we use in textbooks and whatnot. So this is true, true. The third option would be true, false. And the third option will be false, true, and finally false, false. So the homework problem is to, for each option, try to see whether 1 and 2 are true. As it turns out, using the same method we did for the proof of double negation and De Morgan's law, you can actually see the only option that makes the 1 and 2 hold simultaneously is the second one. This is the only option that makes 1 and 2 work. Okay, so if you accept this definition here, if you accept this definition of imply, then 1 and 2 can be regarded as theorems, because these two statements now follows from the definition of imply. Right. However, the way we arrive at this definition is through trial and error. It is not given by God. Instead, you try out this definition and see how each option will lead you to. What sort of consequence do they give rise? So that's actually how the vacuous truths are specified, because this is the only way that makes these two rules, among others, okay, these two rules, perhaps the most important one, the non-equivalence between a statement and its converse. So P implies Q is the original statement, and Q implies P is the converse of P implies Q. Okay, so let me just write those words here. This is converse. Actually, a lot of my quizzes goes like this. So I give a statement, P implies Q, and I also give the converse. Say, is the converse also true? And I make a true and false question, right? Which is, in my opinion, sometimes can be unintuitive. But anyway, so perhaps not as you would first expect. Okay, so converse and the contrapositive. Okay, and speaking of which, let's just give an example of a statement and its converse that is perhaps goes a little bit beyond your first intuition. Is that perhaps not so much, but anyway, I will back up with data if you want to. But it's in one of my community quizzes. So it's a theorem in linear algebra. It's a principal axis theorem. It says if the matrix is symmetric, then it is orthogonally diagonalizable. It's a very important theorem in linear algebra, both theoretically and applied wise. So much statistics and also classical mechanics were built upon that theorem. So that's a principal axis theorem. I just asked the question, is the converse true? If a matrix is orthogonally diagonalizable, is it symmetric? And to my great surprise, I think over half answered false for some reason. I think it has to do with how the statement is usually phrased in textbook. Usually in textbook it just says if the matrix is symmetric, then it's orthogonally diagonalizable. And you don't see the reverse implication. So I suppose that's why a lot of people assume the converse isn't true. But the converse is actually trivially true. If a matrix is orthogonally diagonalizable, that just means, say, P transpose AP is D. So P is orthogonal matrix and A is a symmetric matrix. D is a diagonal matrix. Right? So you can write it as A equals PDP inverse. Not inverse, yeah, inverse also is also true. Transpose in this case is the inverse because of P is orthogonal. Then A transpose would be what? Using this formula for A, you can actually just write down A transpose immediately. So using the property of transpose, it would just be P, D, P, T. It's the same. A transpose is A. It's really that simple. So assuming a matrix is orthogonally diagonalizable, it actually must be symmetric, assuming real matrices, of course. So if you try to find a counterexample of an orthogonally diagonalizable matrix that isn't symmetric, you can't find one. Right? So a converse, not because just because a statement or a theorem in a textbook does not state the converse is true, doesn't mean it's false. Okay, so do the actual verification using definition. So that's the lesson here. So that's the reason for defining imply in this way. It is to cook up, basically, certain desirable results down the road. And actually, so it applies to, yes, principal axis theorem is a theorem for real matrices. So if you're talking about complex matrices, we talk about unitary diagonalizability, not orthogonal diagonalizability. Okay? So when for matrices with real entries, if it is symmetric, then it is orthogonally diagonalizable. And the converse is also true. For complex matrices, we talk about unitary diagonalizability instead of orthogonality. Okay. Instead of orthogonal matrices, orthogonal diagonalizability. Okay, but anyway, yeah, that's a digression. So this is implied. There are actually some odd consequences of this definition. So if you accept this definition of imply, which we do, there's going to be some odd consequences. So remark is that once you have this definition, you can actually show P implies Q, then implies, say, R, is not logically equivalent to P implies Q implies R, where the bracket is placed on the right. You can actually check that using truth table, and perhaps we'll do that in a second. It's the same method using the truth table, but I just want to mention that the operator or the connective imply is not associative, i.e., imply is not associative. So this is an artifact of the vacuous truth. It's kind of odd, but this is what you have to live with. Once you accept this definition, there are some important and desirable properties that you get to keep, and there's this odd idiosyncrasy that you have to live with. So this is not associative. So therefore, formally speaking, P implies Q implies R is meaningless. So formally, technically speaking, this is meaningless. But however, we do see this chain implication a lot in quote-unquote everyday mathematics. Formally, this is meaningless because not associativity, right? It's like, guys, if you've seen vector algebra, we know this operator called, not operator, but operation called cross product. Cross product A cross B. So this is A, this is B, this is A cross B. Okay, horrible looking diagram, but I'm doing things extremely fast here. So it's a common lesson that A cross B cross C is not a well-defined operation. You either have to say A cross B and then cross C, or A cross B cross C, because those two aren't the same. In general, they are not the same. So if there's no associativity, you have to explicitly place your bracket. And when we say things, when we in arithmetic say 1 plus 2 plus 4 plus 11 plus 26, without writing the bracket, we are actually implicitly invoking associativity, because the order doesn't matter here. The order, the way you group the terms don't matter here. If it don't matter, then you can get rid of the bracket. So actually, you can show conjunction and disjunction are both associative. So it's like if you have P and Q bracket, okay, bracket P and Q, and then and R, it will be the same as P and Q and R bracket. So for consecutive conjunction, you can, or disjunction, you can get rid of the bracket. However, if you mix things up, say you want to do conjunction first and then disjunction second, and first or second, the order of the bracket is important. Okay? If you change the order of the bracket, then the meaning changes entirely. There's something called the distributive law, but right now I'm not going to get into that. So the idea is, here, when we talk about implication, formally speaking, this chain of implication, P implies Q implies R, is actually meaningless. But what do we mean when we see this, say in a textbook? P implies Q implies R. In everyday, quote unquote, everyday mathematics, P implies Q implies R actually is a shorthand. Is a shorthand for P implies Q together implies R, and Q implies R. So this is a well-defined operation. Okay, and just to save some writing, we write this. Although this cannot be taken literally. Okay, so yeah. Let's see. Let's do a non-equivalent. So, for example, here, to verify this is non-equivalent, you need, well, first of all, you need 3 atomic variables P, Q, and R. P implies Q. P and Q implies Q, and then implies R. Okay. On the right, you need Q implies R. There's a sub-formula. And P implies Q implies R. So we wanted to look at these two columns. Those are the two we care about. So let's do the truth table. All right. So here, because of you have 3 prepositional variables, atomic prepositional variables, then you should have 8, 2 to the 3, right? 8 rows. True, true, true. True, true, false. True, false, true. True, false, false. False, true, true. False, true, false. False, false, true. And false, false, false. All right? So this is not the most fun thing in the world to do. I can already see Earlier I got 23 viewers, now it's just 14. People get bored and leave. That's okay. That's okay. It's totally fine. So yeah, let's do the truth table verification here. P implies Q, Q implies R, and what do we expect? So true. Let's do the columns first. Okay, each column. Let's do the columns first. So P implies Q is true, true, false, false. Okay, and then true, 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 because of vacuous truth. All right, so P implies Q implies R. Let's just check for the false case. That would be easier, right? So to make this false, you need P implies Q to be true and R to be false. So the second row is a false, and the third row from the bottom is false. Everywhere else is true. True, here, true, 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 false, true, true. Okay? So this is the column that we are going to examine later. All right? Q implies R. Look at the columns for Q and R. Once again, search for combination that will produce a false. True, false. The second row gives you a false. Okay, once again, what's the other option? The third option from the bottom would give you false. Everywhere else is true. Okay, cool. Okay, so there you go. And lastly, P implies Q implies R. What's that? What's Q implied? P implies Q implies R. Well, P is true. Okay, so let me look for the combination will produce a false. Second row is a false. Okay, second row is a false, and say where else is? Actually no. So because that's the only option. That's the only option. So here true. Okay, let me just do things carefully. True, true, true. False is false. True, true gives true. True, true gives true, and true, true gives true. And because the last four rows, in the last four rows, P is always false, so P implies Q implies R is always true. So can we see what's the problem here? Oh, sorry, my bad. They're all true. What am I doing? True. They're all true. They aren't exactly the same, are they? So this column right here and this column on the right aren't exactly the same. And where exactly is the problem? This item right here. Okay, so the proof of the unequivalence, of the non-equivalence, only needs to contain one row of the truth tables. Even though we did this as our scratch work, the actual proof only requires this particular row. Okay, so let me just put it this way. To disprove something, you just need one counterexample. You don't need the whole truth table. So let's write PQR. P implies Q implies R, and here actually you can actually, you know what, let's not skip the sub-formulas. Keep it just like in the original table. P implies Q implies R, and Q implies R, and P implies Q implies R. All right, so yeah, just that exact table where things went wrong is needed in the proof. So you got false, true, false, false, true, false, and here P implies Q is true, P implies Q implies R is P implies Q together implies R is false. Okay, and Q implies R is false, and P implies Q implies R is true. So the two are not the same. All right, so that's QED. That's done. Okay, so basically, this is an odd consequence of, perhaps non-intuitive consequence of the implication, connective or implication operator. Okay, so there's a bunch of expressions for the second, the second column of the last row. Hang on, did I make a mistake? Second column of the last row. The last row, second column, you mean this? The last row, let me check everything, okay? The last row, P implies Q is true. So P implies Q implies R is, oh, right. Did I? Hang on a second. It should be false, 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 right? Yeah. Shit. Guys, what am I doing? Sorry about that. Here it should be a false. Otherwise, the two would make no difference. My bad. So this should be false. Let's redo everything. Well, perhaps not everything, but yeah, thank you very much for catching the mistake. So here, let's redo it. P implies Q is true. P implies Q implies R is, this is false. Yes, this is false. Yes, so Q implies R. Q implies R is true, and because P is false, false implies true is true. So the last, you get another, yeah, this is actually another disagreement. Perhaps that's even easier, right? Perhaps that's even easier. So I mean, this counterexample works, but you just need one counterexample. If you just, perhaps it's easier to memorize the counterexample as when everything is false. When everything is false, then that gives you a counterexample. So when everything P, Q are all false, P implies Q implies R. P implies Q, this is true, but R is false, so left-hand side is false, but the right-hand side is true because of P is false. I think that's even a better counterexample, even though this one works. Let's put that as a remark. This finishes the proof, but if you want extra commentary, you can do that in the form of remark. Thank you very much. So also P, because so how do you say something like the truth value of P is true? This unfortunately does not seem to have a what's that? A universally accepted notation. However, I've seen this. So EV P is true. It's like evaluating P gives you true. Okay, EV P equals true. EV Q equals, EVP is false. Let's say EVP is false, EVQ is false, and EVR is false. That's another counterexample. All right. Yeah. So this is imply. Okay, and you have a bunch of verbal description for P implies Q. So how to read P implies Q? Verbal description. So these are all commonly seen in mathematical literature, even though I tend to just stick to perhaps one, maybe two of them. The most common one for P implies Q is, of course, if P then Q. Actually, this is the one I like the most because I don't think it is possible to create confusion with this one. If P then Q. Okay, so that's one. And also you can say Q when P. I think this is also pretty understandable, right? Q when P. Mathematically, they are the same thing. It's just P implies Q. Same expression, okay? And you can say Q if P. Q when P, Q if P sounds similar, right? And you can also say this one confuse a lot of people. So say it's a P only if Q. So often you will see a statement says if and only if, and there are questions, at least I seen one on mass taxi chain that says, okay, if and only if which direction is which? The only if direction is the forward direction. Let's think about why this is said this way, okay? So, I mean, other than just memorizing it, but only if is the forward direction from P to Q. P only if Q, that's the forward direction. So how does that make sense? Think about that. We said earlier that P implies Q. Remember, P implies Q is equivalent to its contrapositive, namely negation of Q implies the negation of P. Right? We didn't prove it here, but you can use the truth table to easily check that. Okay, so there you go. Here we say Q. P only if Q. Only if Q. That is to say, if Q is not true, right? Just analyze this sentence grammatically, linguistically. P only if Q means if Q is not true, then not P is true. Basically, this one here. So you see, this phrasing actually uses the contraposition, the equivalence between the original statement and the contrapositive. So perhaps this is, I wouldn't call this like super important, but easy to mix up. Only if it's the forward direction. Perhaps pay attention to this one. P only if Q. And also we say P is sufficient for Q. P is sufficient for Q. I think this is straightforward, right? If P leads to Q or automatically implies Q, then P is enough for Q, right? That's the idea. So P is sufficient. We say P is sufficient for Q. For Q. So imagine P is being the president of the United States. I believe to be a president of the United States, you have to be born in the US. Right? If you're a naturalized citizen, you can't be president. I believe that's the case, okay? American audience, please correct me if I'm wrong. Say, this is why people like Arnold Schwarzenegger, even though he could run for governor, he cannot run for president. Right? So we can say if a person is the president of the United States, then he was born in the US. So being a president of the United States is sufficient for being born in the States. Right? I don't know, like, how do you guys? I mean, I guess you can. I mean, if you're American, you don't use this phrase. But in Canada, we say the States when you refer to the U.S. We're going to the States for Christmas, so that means going to the U.S. Simply the States. Okay. Anyway, here the last description would be Q is necessary for P. Once again, this is also an application of contrapositive. Q is necessary for P. Q is necessary. That is to say, if Q is not even true, then P cannot be true. That's the contrapositive. So all these are equivalent verbal description for P implies Q. I tend to just stick to if P and Q or Q if P. Sometimes, maybe occasionally, Q and P. I rarely use P only if Q, except for proving if and only if. Okay, just say, okay, this is the only if direction, and I understood it as P implies Q, but then I just never say it. Okay, P is sufficient and P is necessary. Understandable, but they're too long. I just cannot be bothered. Okay, but when you read this, you should be able to tell what they actually mean mathematically. Okay, so that's the force, right? The force operator imply. Next up we have the actually, you know what? You have more logical equivalence. More logical equivalence as follows. Question. Hi. So many streams these days. I know, right? I know, right? So, hi, Christian. Thank you very much for joining the stream. Yeah. I mean, man, this is the consequence of your action, Christian. So for people who don't know, Christian posted the stream of Leo in my Discord, and I went check it out. So Leo and I started collaborating. So last week I joined his stream on category theory. So he was teaching me some category theory and explained the purpose of it, which was awesome. So go check out his stuff. So yeah, and then I think also on Discord, I got connected with JC. JC Practices Math. Again, awesome channel. And nowadays it's just it's like sometimes we stream simultaneously and sometimes we stream immediately. One of us stream immediately after the other finishes his stream, so it feels like there's so many streams going on. Yeah. Anyway, more logical equivalences. Okay, back to math. One. So P implies Q is equivalent to the not P or Q. Not P or Q. Okay. So the intuition of that is, of course, here we need the bracket. Otherwise, there is ambiguity. So not P or Q. This means if P is false, it doesn't matter what Q is. Right? If P is false, then not P is true. Then here, because of how OR works, right? If one of the statement taking OR operation, taking part in the disjunction is true, then the whole disjunction is true. It does not matter what Q is. So this is saying if the premise in the implication is false, then the premise is automatically true. Okay, so yeah, this is the first equivalence. The second equivalence is the negation of the implication. What's the negation of the implication? Well, how can the negation of implication be true? Well, as we've seen from the table, the only way to negate an implication is to have true, false, true in that order. So the hypothesis needs to be true and the conclusion needs to be false. So to negate that, right, it also corresponds to exactly one scenario, which is P is true and Q is false. The only way to negate implication is to have the hypothesis being true where the conclusion being false. And that's actually typically how we look for counterexamples. So let's say if you're given a statement in the format of P implies Q, and you wish to look for a counterexample, typically we start from a case where Q is false, and then search and try to narrow things down and find if we can make P true. You start from the false part. You start from because that's the only way to negate an implication. So these aren't just fun exercises, okay? They have actual applications when it comes to proof writing. So when you look for a counterexample of implication, start by negating the result, and among those instances, see if you can make the hypothesis true. That's actually how you typically approach, in my experience, okay? How do you typically approach a true or false question? you first try to look for counterexample, and if you're unsuccessful, you try to prove it. Of course, this is just there's no scientific reason to justify. This is how I approach things. Okay, so yeah, if you can't find a counterexample, then look for proof. Right, so that's overall how I approach things. And third one, actually no, not third one. So we can't do the third one yet. But the last logical operator is perhaps the most intuitive. If and only if. So the last one says called biconditional, or if and only if. Biconditional statement also known as if and only if. So to save some writing, we often write if with a double F to mean if and only if. However, I don't think this is now part of the formal vocabulary in mathematics. So when you write proofs, well, formally, try to avoid this. Okay, when you take notes, of course, it's fine, but try to use full sentences. Christian, can you actually use this in formal writing? I don't know. Guys, actually, you know what? Let me check out a book of mine to see, because I can vaguely remember seeing this somewhere. Let me check my... Let me just go upstairs and find a book of mine. Okay, give me 2 minutes. I'll be back. I'm back. Depending on what you mean by formal, I guess I don't think many mathematicians would object to it. Well, like I think everyone understands what it means. It's just like when you say publish a paper or a book, is that acceptable to write IFF? Okay. Actually, yes. Apparently it is. Apparently it is now acceptable because I have this book actually, by the way. If you're interested in multivariate statistics, let me just give the name of the book, because when my channel first got more views, it was due to a series of videos called the Geometry of Statistics and that sort of stuff. But a lot of people ask me about recommended literature. So this one actually I learned a lot from is this one. It's called The Theory of Multivariate Statistics. This one so here I just look at this book again because I remember seeing IFF there. Because this book is actually rather brief. It's quite dense, okay, but there's a lot of results to it. It is not particularly, I would say, accessible or friendly, but it does contain a lot of results. It is worth decoding. But anyway, so I'm saying that in this book, we do see instances of using if and only if, like this. Okay. The other way is to write it as a double-pointed arrow. Yeah, I was saying that it is probably a good idea to avoid using logical operators. I think this is advice by Paul Holmes, okay? Not by myself, but Paul Holmes. So Paul Holmes is rather was rather ambivalent about using logical operator. He was like, okay, imply is okay, and or, unless you're writing a paper on logic, then do not use this. Okay, just for the sake of ease of reading. So yeah, so it's, if I don't know, like at some point it's a stylistic choice. Okay, so Paul Holmes advised that except for imply, we write everything else using even for imply, try to use the actual words. Use the actual words, use full sentences, all that stuff. But if you do write P implies Q, you can give that a pass occasionally. Okay, so yeah, there we go. So basically, that's the kind of the expectation or the subjective taste of a lot of mathematicians, okay, who did a lot of writing. Actually, it's both necessary and sufficient. Exactly, inventive, you're completely right. Actually, we will talk about the verbal description for that. I haven't even written down the truth table yet. So P and Q taken if and only if. So this is interesting, actually. In my original video on the implication, okay, so in my original video on implication, I actually used this operator as justification. Instead of the, hang on a second, instead of this one, the equivalence between converse and contrapositive. So here, when you have P and Q sharing the same truth value, then the biconditional statement is true. Otherwise, it's false. So true, true gives true, true, false gives false, and false, true gives false. Okay, this is completely intuitive. They stand and fall together. Right? Biconditional. Biconditional statement, when you have both false, you get true. So this is finally true. Yeah. Okay. So of course, this conforms to our notion of double implication. So the theorem says P if and only if Q is equivalent of P implies Q and Q implies P. And in fact, this is how you prove biconditional statement in practice most of the time. So you can assume P and then prove Q, deduce Q, and then you do the other way around. Assume Q implies P. Assume Q and then show P. Okay? So what I was trying to say is, remember, I gave all those options for defining imply and settled down to, well, this one, the one you've seen in textbooks, as the only option that will give us equivalence between the original implication and its contrapositive, while at the same time make a implication and its converse not equivalent. Right? So I describe the implication as the only option that makes 1 and 2 both true. And there's an alternative justification. So if we accept this definition of double implication, so a biconditional statement, okay, if we accept this, which I think is rather intuitive, there shouldn't be any controversy surrounding that, even though the last case is still vacuous. Okay, but still, let's say if we assume this, if we assume biconditional statement, you can show that remark. The only in the previously among the earlier stated options, for defining implication, okay, all those options to try out. Among all of them, the actual definition, the one we choose, is the one that makes this equivalence true, but the other equivalence false. So the other equivalence being, I'll write that down soon. So among the earlier stated operations for defining imply, i.e. Vacuous truths, the infamous vacuous truths that creates a lot of confusion. Right? This necessary evil is what the vacuous truth, not i.e., but the vacuous truth definition is the one that makes this equivalence hold. Is what makes P implies Q to be equivalent to Q implies P, P implies Q and P, if and only if Q is equivalent to P implies Q and Q implies P. And P implies Q to be not equivalent to P implies Q or Q implies P. Right? So the last one, if it were true, then would be rather awkward. We don't want the last one to hold. Right? And it turns out that the only definition for imply that makes both work is the one that we defined earlier. So this is to further solidify that the definition of imply is not a random definition that happens to quote-unquote work out. Okay, this is the only one that makes the logic tick, even though it carries some weird consequences like non-associativity. But we decide to live with that, but not to live with, say, implication equivalence to its converse, because that would mean disaster. Okay, so there you go. That's the if and only if, and of course there's also a bunch of verbal statement, verbal description for if and only if. Description. Verbal description. So one is P if and only if Q. The second is P, double F Q. Apparently this is now accepted. Okay, good to know. More words into the language. Right? That's a neat characterization. And the third one is P is equivalent to Q. I think this is used a lot and quite popular as well. P is equivalent to Q. Actually, my personal favorite type of theorem has the following format called TFAE. The following are equivalent. It gives equivalent characterization of one object. Say perhaps the most famous one would be the condition for invertible matrices. There's so many characterizations, man, and it's such a good exercise. Actually, you know what, guys? I'll show you what I'm talking about in a second in the actual module. So let me just finish writing this. Okay, P is equivalent to Q, and P exactly when Q. Right? Another example for that would be in real analysis. In real analysis, there is this big result called the Cauchy's criteria, also known as the completeness of real numbers. It says a sequence of real numbers is convergent exactly when it is a Cauchy sequence. So Cauchiness and convergence actually are equivalent in a set of real numbers. Not in general, but in a set of real numbers, they are equivalent. All right. So, and lastly, you have P is necessary and sufficient, what Inventive just mentioned in chat. P is necessary and sufficient for Q. Because we have P is necessary for Q and P is sufficient for Q earlier, right? So here, if you have double implication, it just means P is necessary and sufficient for Q. Although I rarely say this nowadays, it's just too much of a, it's too long, right? Why don't we just say if and only if, or is equivalent? Those are my two favorites. And speaking of which, my favorite theorem, or my favorite format of theorem, let's go to U-Waterloo linear algebra, linear algebra 2. Actually, it should be linear algebra 1 because that's a fundamental result in the earlier part of the course. Invertible matrix theorem, whereas inverse, matrix inverse. Inverse, right here. What? What? Okay. Okay. Inverse of a matrix. Inverse is unique. There's a bunch of characterization for invertibility. Yeah, inverse matrix theorem. Yes, this is one of my favorite theorem of all time. Because of this format, there's so many equivalent characterization of invertible matrix, and it's an excellent exercise to prove them. So typically when you prove multiple equivalence is you prove 1 implies 2, 2 implies 3, and so on, all the way to 7 implies 8, and then finally 8 implies 1 to complete the circle. Okay? Everything is equivalent. So it doesn't mean everything are true. Everything is true here. It just means if one of them is true, everything else must be true. They stand and fall together, right? Like in the table. Right? If and only if is true doesn't mean P and Q are both true. It just means they have the same truth value. Because when P and Q are both false, the biconditional statement is also true. All right? So there's that. And actually, why do we spend all this time talking about logic? It is because the logical structure of a statement dictates how you would approach a proof. The most common type of proposition that you will see in mathematics is the third type, implication. That's why we spend so much time discussing this one. So a general format, okay, a very vague format to prove P implies Q is start with saying assume P is true, need to show Q. Right? At the surface, it feels like, well, nothing seems to have done, right? You just literally restated what you want to do. But now you have broken down the pieces. You stated what you assumed and you stated what you wanted. You can now start to unpack the meaning of each statement. Okay? It's like in our little example, the product of two integers is odd. That's one statement. Of course, that's one statement. That's one sentence grammatically. Right? So you can start the proof with let m and n be integers, assume m and n are odd, and also a sentence that follows that would be, especially for beginner, I think it's extremely helpful, is to write need to show m times n is odd. Right? I still have this habit, especially when I approach complicated and new fields. So, but because of most mathematics have this format, if such and such and such, then such and such and such. When you approach a proof, you can always break things down into hypothesis and conclusion. And it helps us digest and just comprehend what is going on by separating them into different statements, into different sentences, assuming, hypothesis, and then need to show what. And also need to show has such a powerful, so to say, purpose. It's a powerful purpose because if you don't write need to show, it confuses reader. Are you assuming m times n is odd already? Or are you working towards this goal? By writing need to show, then it is automatically clear. It is automatically clear that you're not assuming m times n is odd, right? So you're trying to build a bridge between them. And then you can say, okay, what is the meaning of odd numbers? Right? The meaning of odd number will play a part in both in terms of using the hypothesis and verifying the conclusion. So you now have a little bit of a clue of how to approach the problem, right? So that's the logical structure of implication. So if you see a statement is implication, and even if you don't know how to write the proof, just start by assuming the hypothesis and also your goal, and then unpack the terminologies and see if there's any relevant results that leads to the need to show part. So these are baby steps we can make. And next you have the if and only if part. If and only if. So if you see a statement if and only if, immediately you know, oh, I probably need two directions. So you can lay out your proof into two separate sections. And sometimes, quite often, one implication is trivial. So you can immediately get some easier work done. Quote unquote low-hanging fruits, as they call it in research. Right. So I was doing the measure series stream yesterday. So there was this problem of describing an object called the sigma algebra, which is a collection of subsets, in two equivalent ways. Right. So that essentially boils down to an if and only if statement. So it helps to think whether one direction is readily available. And now you just narrow down your effort, concentrate your effort on the other implication. So that's why studying logic is a prerequisite for doing formal proofs. Okay, so this helps you clarify your thoughts. Okay, and there we go. There's some. Okay, so right now we're at. I think we started at 2, so it's only 2 hours and 45 minutes. Okay, it went a little bit of a bit beyond my expectation. Actually, I was expecting to spend much more time on this, but that's a good thing. So far we described a few things. What's a statement, and what are connectives? Okay, and these are part of propositional logic. They are important, however, its language is rather limited. For example, you cannot do calculus with it. You cannot describe calculus with it. Why? Because calculus involves limit. And for defining limit, you need other ingredients of logic called quantifiers. Okay, we will see an example. But first, let's talk about quantifiers. So here, so far, we've only introduced propositional symbols, truth value, truth table, and connectives. And now we're introducing another important ingredient in logic called quantifier. And that's pretty much all you need when it comes to logic. For everyday mathematics, if you study mathematical logic, of course, things are a lot more in-depth. Okay, but here this is for general purpose mathematics. Quantifiers. There's only 2 quantifiers. So here, this is where things we're going to introduce sets here. Okay, of course we will do dedicated lessons on sets, because here we just have to introduce the notion of a set, and we treat it as a primitive notion. We're not going to bother defining what a set is. That's the subject of formal set theory or axiomatic set theory. We're just going to treat set naively as a primitive object, a collection of things. Okay, so definition, quantifiers. So here, let U be the universal set. Be a universal set. This is the set of objects of consideration. This is a universal set under consideration, and Px be Px be a predicate. So what does that mean? Remember earlier we gave an example, m plus 1 greater than 3. That's not a statement because its truth value depends on a free variable, and this is exactly what we're talking about. So if you fix the value of x, then p of x becomes a statement. It will have a definite truth value. But for a general, not a statement, but just a sentence, p of x, it will not have a it will not have a truth value on its own. U be a universal set and px be a predicate. The statement for all x px, for all x, sometimes you just say for all x, but what we really mean is for all x in U, in the universal set. P of x is true. Or you would say just P of x. You can just say P of x, or you can say P of x is true. Both are okay. So here in U can be omitted if the U is clear, and its true is also it can also be omitted. So for all x in U, P of x is true. That's what we call a universally quantified statement. The second one says there exists x such that px is true. So there exists just two quantifiers. For all n there exists. For there exists x in U, px is true. Once again, you can just say there exists x, px. That also works. Okay, and the notation for that would be for all is a upside down big A. Or is an upside down big A. In U, you use this notation. Use this. This looks like an E. This looks like some kind of font for E. Right. Means being an element. For every x in U, P of x. So typically we also can put a bracket here. It appears to have no universally accepted notation, but you put bracket whenever you think there's a possibility for ambiguity. Okay, so I recommend putting the bracket, but in practice we often omit the bracket when there's no risk of ambiguity. Is E a set? What is E? No, this is just a symbol for is in. X in U, this reads for X in U, okay? So when you read this, this says that the element X is in the set U. This is not a set, it's just a relational symbol. Okay? It's just a relational symbol. This is not a set. Yeah, it's the E symbol is simply a shorthand for belongs to exactly. Christian stated perfectly. So X is in U, exists X in U, Px. And once again, if the set big U is understood, then you can omit this in U. Simply say for all X, Px, there exists S, Px. So these are quantifiers. So the first one is called a universally quantified statement. Universal quantifier for all. And that's really all you need for the majority of mathematics. Even for extremely complicated subjects, esoteric subjects, this is all you need. It's kind of amazing that insanely intricate machineries can be described using just a handful of vocabulary. There exists quantifier. So some of you might know I started in the morning I started doing Russian practice stream. I don't know how long I can sustain that effort because right now I'm on vacation. I hope I can still continue that because language learning takes consistency, right? Just like in mathematics, right? So, of course, learning a foreign language, especially one that is as complex as Russian for, well, non-native speaker, is going to be, it's going to be takes a lot of effort. However, because of the nature of mathematical writing, you only need a very small set of human vocabulary to describe extremely complicated things. I think that's a doable task because this is such a restricted objective, right? We're not trying to master conversational skills. We're just trying to read mathematical literature. And for the most part, mathematical literature, the language used, the vocabulary used is highly restrictive, just to avoid ambiguity. I practiced from How to Prove It a while ago and I can't recommend it enough. Yeah, it's a good one. What book you are following for this? Well, I'm following this one, The Tool for Mathematical Reasoning. Once again, I like the book personally, and I actually, to be honest, I don't know many introduction to proof books. This is the one I use. I like it because it's quite succinct. It's barely over 200 pages, and it covers decent amount of material. So, and the materials covered here are shown on the table. Language and logic, here we are. Proof techniques, set and functions, basic numbers theory, equivalence relation, cardinality, and real numbers. So with these basic tools, you are well prepared to study something like analysis and topology and abstract algebra, that kind of thing. Of course, along the way, you probably need more. You need to have supplementary, so to say, supplementary topics in set theory, for example. But they will carry you a long way. And actually, I do hope after we finish the fundamentals of proof writing, we will get into, say, the first 2 chapters of Baby-Rudin, and after that, some point set topology in Moncrief. Okay, really, a lot of the proof skills in advanced mathematics is just masterful command of fundamentals like what we're doing here. Is E an element? No. So here, let me just give you an example. So 1 is an integer. To say 1 is an integer, we write 1, this E symbol, E looking symbol, Z. Okay? This is a full sentence. It means 1 belongs to the set of integers. Actually, if that's not clear, let me start with so here, let me just type it out. Okay, so 1, you write in the set Z. Okay, yeah, this is Microsoft Word. As you can see, this is the equation editor. Like, this is easier than LaTeX in my opinion, but less powerful. But of course, I think it's sufficient for most purposes. For practice purposes, it's not good enough for writing a paper. But for note-taking, this is completely adequate. And it has the advantage of what you see is what you get. And a lot of the codes are the same with LaTeX. Okay, so, and sometimes it's easier. For example, you say you just want to write a fraction. In LaTeX, you do this frac thing, right? And then it will render. So, but here you just say 1/2, and then will be there. So sometimes it's actually quite easier. And you can do things like summation, integrals, sum from I1 to n. Sorry, not this. So something needs to be a little bit get used to is you don't have that many curly bracket going on in MS Equation Editor, or AI, right? Anyway, I'm getting distracted. So basically, here, this is a relational symbol. This is not an element. This is not a thing. Okay, 1 is an element. Z is a set. This is just to state the relation between the two. Right. So yeah, this is a relational operator. So if you go to say equation and you drop down and see the drop down menu, there's this category called operator, and there I believe you will see the in symbol. It's not an object, okay? It's not an object. It's not an element. It's not a set. It's just to state the relation between an object and a set. Say, we can say, well, 1/2 is not an integer, so you can write 1/2 not in z. Okay, you got it? It's like an equal. It's kind of like equal sign, right? You wouldn't consider equal sign an object on its own. It's just a relational symbol. So E does not exist. What do you mean? Yeah. Yeah, so yeah, sometimes everything in math is a set. Yeah, I guess we have no one else to blame but ourselves, right? So this is a relational symbol. This is a relational to indicate, say, I am a Canadian. So you're indicating a relationship between two objects. I am not American. It plays that kind of role. It is not an object on its own. Is that clear? All right, so we'll skip that. All right, so basically that's quantifier. Anyway, so here we have the quantifier. To practice this, let's do some exercises, all right? We will, actually, I'll describe the word. Describe a sentence in Word. I will not write all on the board because this just takes a lot of work, but I'll state it as clearly as possible, and I'll write down its symbolic format. What do you mean by American? Well, I'm citizen of the United States, okay? Okay. Yeah. So, anyway. Okay. So let's go and take a look at examples. First example. There exists a natural number n such that n plus 1 is greater than 3. So how do we write that in symbols? There exists a natural number n such that n plus 1 is greater than 3. So we would write it as such. 1. Exist n in the set of natural numbers. And by the way, perhaps it's a good idea to introduce a notation of several sets. Okay, before I do these examples, I'm just gonna put the number systems here. Okay. Number universes or number systems. Number system, notations. These aren't definitions, just notation. Number system notation. Let's see. The most common ones, you have the natural numbers. Actually, this one is controversial. Leo, I know you're in chat. Tell me, what's your starting natural number? Is it 0 or 1? Like for you, what's your starting natural number? I'm going to take n starting from 1, okay? Because I'm a filthy analyst. Just joking. So natural number in our convention start from 1. I know computer scientists and algebraists sometimes start from 0. In America is 1, in Europe is 0. Wow, are you serious? I thought it was a different convention across discipline. I thought analysts and computer scientists, analysts start from 1. If I could, 0 is clearly the better answer. You see, Leo is a algebraist and computer scientist, whereas I'm more applied mathematician and analyst. So I'm used to starting from 1. And even to this day, when I code in Python and I write this freaking NumPy array, I sometimes forgot, the index actually starts from 0. And it bothers the heck out of me. you know. Whereas in R, in the programming language R, the statistical computing language R, as well as MATLAB, you start from 1. But in Python, they start from 0. Oh, okay. Natural numbers start from the empty. Well, that's a construction. So the set of natural numbers. We'll do that in a few seconds. We'll discuss in a few seconds because this always triggers some debate over this. All right, integers. Here we're just giving notations, okay? Because we're going to use it in our example. The integers is this double strike, big Z, okay? I think it comes from German. I don't know the exact word. I think it has to do with the word whole, like entire, whole. -3, -2, 1. So it contains all the positive and negative integers as well as 0. Okay, so the set of integers and rational numbers. So these are the most common type of numbers we will see in this series. We're not going to see much complex number, if any. So rational number is Q. Q, by the way, we already see some set notations already. Hopefully this is not too confusing. But basically, you can describe a set in different ways. So for the first two sets, the set of natural numbers and integers, we describe the set by listing its element. And of course, there's this confusing symbol of ... What does that mean? Well, it usually assumes a pattern continues. Right? So, but it really depends on, okay, what's called a pattern you are talking about, right? If you wanted to indicate that. We assume the reader already knows what is the pattern, okay? 1, 2, 3, 4, and so on. So here, the two ... in the set of integers also assumes the reader knows what pattern should be continued. Q, however, even though it can be, actually is a major result actually later on, even though you can, in principle, list all the elements in Q, we typically don't do that when we describe the set of rational numbers. Instead, we say Q consists of numbers of this form, m over n, where m and n are integers, and n is non-zero. The set of fractions whose numerator and denominator are integers, and the denominator is a non-zero integer in particular. And lastly, you got the real numbers. The real numbers is perhaps the hardest to define, even harder than complex numbers. So assuming you understand real numbers, complex numbers is actually very easy. But to go from rational to real requires a lot of work. In fact, it took over 2,000 years for that to finally clarify. And even nowadays, some people don't accept real numbers, even on YouTube. You guys probably know a few examples. All right, I haven't been reading chat. I'm just writing notations. Okay, the set of R is once again, this is informal description. Is the set of X has a decimal expansion. If X has a decimal expansion, okay. Once again, completely unrigorous, because we haven't even defined what decimal expansion means, but we're just going to take it for granted from now on, okay? And we will, in the actual proof portion of the series, we will say, we will give the fundamental properties of R. And we never really need to work with decimal expansion. Okay? Decimal expansion is a particular representation of a real number. It has nothing to do with how the real numbers operate, okay? How it represents a member of the continuum. And actually, defining real numbers is one of the last goals of this series, because defining real numbers takes a lot of work. Okay, all right, so these are the notations for number system. And guys, chat has been rolling like crazy. Let me look at them and see what you guys been up to. All right, so hold on a second. Okay, you were saying that in America is 1, in Europe is 0, regarding the starting number in a set of natural numbers, right? So yeah, I tend to regard n start from 1. That's my bias. So I get uncomfortable when Python NumPy array start from 0. Okay, but anyway, small thing. So yeah, mostly it doesn't matter, but in a few cases it doesn't matter. You almost always want 0 index. I see. So an example in analysis is how we define sequences, right? In sequence, we define a sequence in analysis as a function from a set of naturals to, well, whatever set your sequence takes values in, right? So it would be, so you can think of f1, f2, f3, and whatnot. So, analysis almost always start the sequence with the first index being 1. Okay. So Leo does not like R. What is 1 though? Yeah, it's a good question. Actually, inventive. You're very. It's very. Because right now I'm just using definition. I'm just not using I'm just using notations. I never define what these symbols mean. I'm doing this for a reason, because I figure at this early stage, because this is meant to be an introduction to proof for beginners. By beginners, I don't just mean like just beginners for proof writing in general. Let's say you can still be a beginner and have taken, say, calculus and whatever. So if you haven't done much formal proof writing, this is still like a course for you. Okay, so given that in mind, let's say if we start by defining natural numbers axiomatically, it would just feel like a pedantic exercise, and it feels completely detached and just rather dry. So I think it is safe for us to assume that everybody who's seen this, or doing this series, knows exactly how natural number behaves. You know exactly what the ... mean, and you know exactly how to perform arithmetic for integers, rationals, reals, and whatever. Okay, so I'm not defining 1, right? So I'm not defining 1. In fact, can mean different things in different sets. There's no definition of 1, actually. Or should we say there's no universal definition of 1. It really depends on which set you're talking about. For example, in a set of natural numbers, right, 1 is, in a set of natural numbers, 1 is you can think of it as the base case in the induction. 1 is the base case in induction. And so basically, these aren't just collection of things. The number system aren't just collection of objects, but rather collection or sets with structures on them. The set of natural numbers has only one structure, the successor structure. What do we mean by that? A structure is it tells you how the members of a set are related to each other. So 2 is a successor of 1. 3 is a successor of 2. In fact, learning how to count can constitute exactly of knowing what number comes next, right? So there's only one structure, that is the successor structure on the set of natural numbers. So for that, you need a base case. And the base case is called 1. Right? However, say in rational number or real numbers, there's no successor structure. You cannot say, okay, given a natural number, given a rational or real number, what comes next? There's no such structure. So instead, 1 is defined as the so-called multiplicative identity. It has the property that for any rational number or real number x, x times 1 is x. Okay, so for rational and real numbers, instead of having a successor structure, you have arithmetic operations. Arithmetic operations, addition and multiplication, which satisfy a certain axiom that allows you to also define subtraction and division. And also there's the order structure. Anyway, so number system is a separate topic on its own. You can entirely make a separate playlist or book, actually books, yeah, whole books have been written on number systems alone. How do you construct numbers from out of nothing, like almost out of nothing, from sets and whatever? Okay, you got the axiomatic treatment of number system, or you got the more constructive treatment of numbers. So it's a hugely complicated topic, actually. And right now, we're not going to be bothered getting into those, although eventually we will discuss how real numbers are defined, assuming the rationals is understood. All right, so we're going to define real numbers assuming the rational is understood near the end of this, at least, I mean, these are the goals for the series, okay? But defining real numbers is actually, you already need to know a lot of proof-writing mathematics to be able to understand the definition of real numbers. All right, so the modern definition of real numbers boils down to 3 words: complete ordered field. But, well, to understand that, you need a lot of background in set theory and proof-based mathematics. All right, so what's chat been up to? Z is for Zalon, i.e. numbers. I see, okay, right, Z means Zalon. Thank you so much. So Q is for rational? What the heck is that? I always thought Q is like quotient. C is for complex. Yeah, it makes sense. Hoctonian. You mean quaternion? Quaternion uses H. I believe it's for Hamilton, the discoverer Hamilton. Even though we're not going to be dealing with quaternion in this stream, this is not 3D rotation for game and graphics engine development, all right? So go check those out. So check those stream recording out if you're interested in 3D rotation, that sort of thing. I hope to use that as an invitation for Lie theory or something like that. Also very fun stuff. Anyway, so yeah. Okay. I saw some poo-poo on Norman Wahlberger. Okay. Anyway, so yeah, he's an interesting fellow. Let's just put it that way. I mean, he does have useful stuff, you know. And I do recommend you check out his point of view. If you can take out the personal emotions out of the equation, then it's a pretty unique point of view. Yes, you can define real with decimal expansion. It is not impossible. You can certainly do that, actually. You can certainly define decimals with, define reals with decimal expansion. There's nothing wrong with that intrinsically. It just, well, aesthetically, it's perhaps less pleasing, right? You know, I've been doing this tensor calculus series, and I got roasted for not using the modern definition, the quote-unquote coordinate-independent definition of tensors, because I've been using the indices notation, because I feel like, well, in the applied field, you quite often need to be able to work with coordinates, right? And then after that, you can abstract things, right? It's like in linear algebra, you first learn how to compute with matrices, and then learn the definition of vector space. At least that's the order I learn it, of course. That's my own bias, but I got roasted for, oh, you don't really understand tensors if you only use index notation. I was like, whatever. Yeah, it's like you can define reals with decimal expansion, but it requires a choice of base, right? The base of 10 is rather arbitrary. Actually, if you even when you just use an arbitrary base, even when you just use an arbitrary base, this is still arbitrary. The structure of decimal expansion is still arbitrary. It's not from that, it is not immediately clear what is the distinguishing feature between the real and the rational. We know that from high school, rationals are decimal expansions with repeating digits, right? And reals don't, in general, don't repeat. But how does that explain, say, how does that explain, say, the real numbers has this least upper bound property? It's not immediately clear. So mathematicians tend to prefer more quote-unquote intrinsic definition. That is to say, defining real numbers that has nothing to do with this representation. Right? So yeah, certainly there's nothing wrong. You can define the real numbers the high school way and commit to that definition and prove properties with it. Although it's kind of awkward to define, say, multiplication with two infinite decimals. Right. So anyway, here real numbers are list of all points on the line. Actually, that's the correct intuition, right? So the whole project of defining real numbers rigorously is to formalize the notion of a continuum without geometric intuition. So yes, I don't agree with Wildberger, but introducing the real is by far the wildest step. Yes, exactly. Introducing the real is extremely difficult, well, in comparison to other constructions. So if you go from natural to integer and then from integer to rational, they compare nothing to the amount of work needed for going from rational to real. Okay, and it took over 2,000 years for mathematicians to realize this must be solved, or at least formally addressed, because over centuries, even though there was a realization that the real numbers is problematic, it tends to get swept under the rug. Okay, so it wasn't until the mid of the 19th century when intricacies of Fourier series became just too wild to be understood, that mathematicians starting to look at fundamental notions like numbers and functions seriously. The definition of function came from the investigation of Fourier series. The modern definition of a function came from the investigation of Fourier series. The modern definition of integral came from that. The modern definition of real numbers came from that. So Fourier series is extremely fruitful mathematically, even though it was started as a purely applied tool for understanding wave motions and heat transfer, and it bears so much fruit in pure mathematics. Anyway, so let's continue looking at chat. Yeah, falling down the hole of what is one will lead to the philosophy department. You'll quickly get what is and find yourself stuck at what. Yeah, in modern mathematics, we typically aren't bothered with defining single symbols anymore. We don't take the question what is one seriously enough. And for good reason, because it's just a symbol. Typically, one is only defined in relation to other objects. Okay, one is only defined as because I mentioned one can be seen as a base case in the set of natural numbers, or as a multiplicative identity in, say, fields, like rational and real. So these are all defined relationally. As usual, the answer is depend, exactly. All right. Yeah. Okay, so yeah, and finally we can now turn to the examples of universally quantified statement. We can say something like this: there exists an n in a set of natural numbers such that n plus 1 is greater than 3. This is a universally quantified statement. Okay, actually, I didn't finish the definition. My apology. The definition says these two kinds of statement are considered as statement in the sense that they are propositions, that is, they have exactly one truth values. Okay, these are statements. These are considered as statements, valid statements, i.e. sentences with truth values. All right. How dare you exclude 0 from natural numbers? I know this is going to be controversial. So, yeah. Fellow analysts, back me up. We need to stick together on of this vicious attack on the set of natural numbers. Yeah. So anyway, second, we say. So the first one is obviously true. This is a statement, and it's true. It is a statement. So it's a true statement. Okay? It's a true statement. Okay? Second, the set of real numbers. If for all x in real, x squared is greater or equal to 0. This is also true. True statement. And by the way, guys, we were just talking about number system. Why don't we give a few recommended books on number system? If you're interested in this stuff, I have a few books to recommend actually. There we go. We have the there's an old but gold one. I think it's written by Landau, not the physicist, not the Russian physicist, but the German number theorist called Edward Landau. Edmund Landau, right? Edmund Landau. I believe he was a friend of Einstein. Yes, Landau, The Foundation of Analysis. And I believe this book is in public domain because it's written a long time ago. Edmund Landau, The Foundation of Analysis. How come it's only 16 pages, huh? Yeah, this one, The Arithmetic of Whole, Rational, Irrational, and Complex Number. It's still surprisingly readable. I don't know if it's in public domain already, but basically, yeah, this one is a very thorough treatment of number system, going all the way from natural numbers to complex numbers. And of course, the hardest part is to construct real numbers. I mean, this is not a full book, but I think you can easily find full text on the internet. So this one, the one by Landau, Edmund Landau, number theorist, foundation of analysis. This one is dedicated treatment of numbers system. Amazing stuff. It's a classic. And I also believe there is a book written by Mendelssohn, who is a logician. Edmund Landau, Foundation of Analysis. Go check this one out. And another one written by Mendelssohn. Mendelssohn. How do you spell his name? Called The Number Systems. Yes, number system and the foundational analysis. So this one, I think, is a tribute to Landau. It's a more modern treatment. So here, it starts from logic, just like we did. Of course, in much more depth, because the author, is a logician. Okay, so this one, I think it's a Dover book. I'm not sure if it's still available, like it's still in print. But try to look at this one. If you're interested in number system, the foundation of analysis, strongly recommend you go check out this one. Okay, also a great book. So, all right. I once met a logician. It was very disappointing. Did no card tricks or anything disappear? Right. Anyway, so yeah, mathematical logic is fascinating. Mathematical logic, I wish I knew more about it. So anyway, let's continue. So 3. I believe Kolmogorov also wrote a text on mathematical logic. I should have checked. I should check that. I'm not even sure if it's translated into English. Kolmogorov's work on mathematical logic. The third one says for all n in big N, Introduction to Mathematical Philosophy by Russell. Well, hi Hiroshi. Thank you very much for joining the stream. Yeah. So yeah, I don't know. Like, is Russell's paradigm still considered like rigorous or still? I mean, of course, it's influential. I mean, it's like, you know, Newton's Principia is a monumental work in the history of calculus, but it is considered antiquated, right? When it comes to the notations and whatever, it's still worth reading as for historical purpose reason, right? So is it still like Russell's work is still like currently the standard mainstream mathematics, or we already moved beyond that? So yeah, be very, I wouldn't say wary, or before you read a monumental book like those ones, it's better to consult opinions from experts or somebody who have experience in the field. Like, is it worth your time, and what are you getting from it, that kind of stuff. All right, so 3 is a statement, but it's false. It's a false statement. And Hiroshi, I know he's biased towards British mathematics. So take what he says about British book with a grain of salt, guys. All right, I don't read. I can just don't read. Okay, fair enough. But you can watch video, so that works too. For all x in real, so this is a more complicated statement. So it says x cubed plus 52x squared plus 79x plus 1,000 greater or equal to 0. Plus 1,000 greater or equal to 0. So that's, of course, it's a statement. Yes, it is a statement. But can you think, can you decide whether this is true? Right? So the first one is a little bit trickier, right? So it's not as obvious as the others. For all x cubed plus 52x squared plus 79x plus 1,000 is non-negative. Is that true? Well, you need to explore this sort of questions. Think about how cubic function behaves. Right? So the cubic function tends to infinity. Well, here, because it's a monomial. No, it's not a monomial, but sorry. I was trying to say that the polynomial with coefficient 1 in its highest coefficient. I forgot the name of it, but basically the cubic function here, this one, should tend to infinity as x tends to infinity. And should tend to minus infinity when x tends to minus infinity. And in the middle, it can maybe curve a little bit. But here, it's already enough for us to decide the statement. It's impossible for all the x to be, all the x in R so that the cubic polynomial is greater than or equal to 0. It's impossible. Right? Here. So how can we construct a counterexample? It's not enough to give this kind of vague picture. Although it's excellent intuition, we still need to find a concrete example. find a concrete example. So, I mean, perhaps a natural method is simply to take an x that is super negative. You try an x that is super negative and see if it is negative. We know qualitatively if x tends to minus infinity, it should be negative. I guess you can just keep trying big enough numbers, right? So because of the constant is a 1,000, why don't we try? Okay, try x equals minus 1,000. So x cubed plus 52x squared, because you want the cubic term to dominate. That's the idea. And then plus 79x plus 1,000. And you simplify that, okay? Just do the algebra, and I believe this is less than 0. So that's a counterexample. Example. So we have 20 minutes left. I just wanted to talk about how do you start with a proof. How do you start with a proof? Okay, we'll talk more logic down the road. The next stream is not yet scheduled, but let's say we've seen all these type of statement. How do we say start with a proof? Okay, I mean this is gonna be it's gonna sound a little bit bureaucratic. Okay, see this pattern, start with this sentence. It feels like some exam prepping tricks, but that's not the point. You have 20 minutes and we all die. I promise you will not die in real life after the stream ends. Okay, Hiroshi actually, I don't think there are many errors, but either way, it's just an introductory book that works mainly for the motivation it provides to study the fundamental. Okay, it's also a book reading to relax. Wow. Reading Russell to relax? Okay. Good for you, I guess. That's awesome. So, I'm just going to give some common format of how to proceed a proof. Okay, so this is perhaps, as I said, a little bit bureaucratic, but it's because of these baby steps that we make that ease the overall general fear and frustration when it comes to proof writing. Because proof writing is a highly nonlinear process, unlike, say, calculating an integral series or things like that. It takes trials and errors, and there's no algorithm. I mean, unless you study things like proof series, it's going to be automatic proof writing algorithm and things like that. But I'm just saying that as a human being, how do you approach a proof? It really depends on, first of all, the method you would like to choose. Is it a direct proof or indirect proof? And the structure of the statement. Okay, so actually, let me just write the tips for finding proofs. This is the general principle for proof writing, and will help you a long way. General principles for proof writing, or you can think of not proof, but just template for proof writing. Not just principle, but also proof writing. Okay, this is not just some vague principle. You can actually apply this immediately. Template for proof writing. Okay, so the first thing is, if we wish to prove a mathematical statement, we first determine the logical form of the statement. Determine the logical form of the statement. So that's the first thing we can do. And you can do this without even knowing what on earth the content of the theorem is about. Just a logical form. Is it an implication? Is it an if and only if? Is it an existential statement, or is it a universal statement? A heuristic for proof. Actually, heuristic inventive, I think you mean the sketch of an argument or intuition for an argument. But heuristics and proofs are treated very differently. Okay, so typically heuristics aren't considered rigorous. For example, in my stochastic calculus series, nothing is rigorous. Okay, but it doesn't mean the series is worthless. At least I don't hope so. Okay, I mean, perhaps it's just worthless to you, but the idea is heuristics can skip certain assumptions and even have gaps in the logical reasoning, and perhaps use a geometric reasoning and some physical argument, that kind of stuff. But none of those constitute as valid method in mathematical proof. I swear, it is introductory book. It has more words than mathematical symbol. Russell's difficulty is principial. Not this. Okay, great. Okay, thank you, Hiroshi. I'll check those out. Okay, I'll check that particular book out, Introduction to Mathematical Philosophy. Actually, it's philosophy, right? Perhaps that's the reason. It's not mathematics, but rather mathematical philosophy. Okay, I'll take a look. Even though I think traditionally, I'll see if this changed my mind. Because traditionally, I'm kind of put off by the more academic mathematical philosophy. I just find them to be rather dry. Like, is mathematics discovered or invented? Like, I mean, who cares? Come on. I don't understand why people are spending time on it. Okay, it's perhaps just my pure ignorance and audacity to say that. But for me personally, as a personal note, I consider myself a philosophical person, but I'm just never so interested by the debate about the foundations. I mean, not the foundation of mathematics, but the philosophy of mathematics. I know they're connected, but I'm more interested in, when it comes to foundational stuff, which I'm very much ignorant about, is, let's say, what kind of paradoxes does, say, the set theory, the naive set theory would lead to, that kind of thing. I would still consider it to be mathematics, not philosophy. So I was saying, like, I do consider myself to be a more philosophical person, but traditionally the topics of, say, Platonism, formalism, logicism, and intuitionism, that kind of stuff, never really interests me. I don't know, like, for a reason. For philosophical things, I'm more interested in, say, 20th century and perhaps even 19th century existentialism, which I think mathematicians should talk more about. It's like, I'm interested in how do mathematicians relate to his or her work? Okay, is it like a way of life, or is simply intellectual output? All right, and what does doing mathematics do to a person? So, in what way does it help the development of human character? That sort of thing. That's what I'm interested in, and the general relation between mathematics and human society as a whole. Right. So yeah, Leo has been very providing. Has been. So Leo is telling me a lot about naive set theory and logic. Okay. Yeah. So that's indeed very. I do see a lot of online debates about how. Like whether mathematics is discovered or invented. Even professors hold seminars over it. You can search it up on YouTube. Is math invented or discovered? I never seen the person in real life, like, who is, say, strongly philosophical about a certain position. For example, Platonism. Platonism in mathematical philosophy insists that mathematics exists independently of human mind, right? It exists objectively out there, right? And then the mathematician's job is to discover its structure, right? Right? So, I mean, it's less tangible, say, um, compared to discovering a new element in nature, but it's still fundamentally the same. This same. I'm sorry to say, it's the same kind of discovery. Okay, it exists before human beings existed, and it continues to exist whether we like it or not. Right? So that's sort of the position of Platonism. Anyway, so I guess we can skip that and talk about the general principle and template for proof writing. So this is a very practical manual. First of all, determine the logical form of the statement. Is it implication? Is it a by implication? Is it existence statement, or is it universally quantified statement? Okay, so for most of the proofs, most of the proofs in mathematics are direct proofs, if I can say that, okay, because I never done any statistical analysis for that. But in my experience, most proofs I've seen are direct proofs. Okay, indirect proofs exist, and they're super important. And in particular, proof by contradiction is a form of indirect proof. That being said, most of the proofs are direct proofs. So, direct proof of, say, if you want to prove P implies Q directly, okay, in this format, what do? You begin with assume P is true. Begin with assume P is true. Once again, this sounds very bureaucratic. All right, you just spot the structure and write the beginning sentence as if it's a machine-generated content. All right. So, but this is going to help you disentangle what is the assumption and what is the conclusion. Assume P is true. Write that down. And then demonstrate. Proceed to demonstrate. And then proceed to demonstrate Q is true. So also perhaps need to show Q. It also gives you tips, because in order to show Q, do you need to use a definition, or do you use a previously established theorem? It forces your brain to look for options. Okay, and then proceed to demonstrate Q. Okay, so when you see a format of this form, okay, P implies Q, begin with assume P is true and need to show Q. Hard to go wrong with this startup. Okay, so here, yeah. Okay, so indirect, will there ever be a quiz? Well, we have quizzes every day, but due to the format of YouTube quiz, I cannot literally ask you to write proofs. And I mean, you can do that in the comment section, but I guess this is too much for most people. So instead, I just pose true and false question, which in most circumstances requires some sort of proof writing. Okay, anyway, proof writing of searching for counterexample. So I think that's the compromise there. And because of the character limits of the YouTube quiz, it forces me as well to write mathematics clearly and succinctly. It's almost like sometimes I often feel like I'm not giving complete proof, but rather just pose signs. Right? It's like I highlighted the path of reaching a certain result. I just post like, this is what you should reach, verify this, do that, and get the full proof, and within a 500 character limit. Right? So I got to do that stream where I do all of Ming's quiz question. Oh, thank you so much, Leo. Thank you so much, Leo. Hope you enjoy. Anyway, so yeah, this is the direct proof format. And then what about direct proof for all x px. Once again, this is also extremely common for all x px. And we will see that in calculus, actually. We'll give the definition of a limit near the end of the stream. We're already near the end of the stream. We'll fix that. We'll give the definition of a limit, and we will next time we'll do a proof of limit. Okay, good old proof in analysis. Beautiful in my opinion, although often despised by algebraists. So anyway, so all x px, we begin with what? Let x be an arbitrary but now fixed element in the set. Of course, that's a long statement. Okay, the full sentence should be, let x be an arbitrary but now fixed. In the bracket, okay, it's treated as arbitrary but now fixed element. In the universe. In consideration. In a universe U. Okay, so this is the beginning sentence of proving for all x px. And of course, this is a long statement, so sometimes you can just say, the shorthand would be, let x be arbitrary. If the set is obvious, if the set U is obvious, you can say let x be arbitrary, or let x be in U be arbitrary. Let x in U be arbitrary. But very often we just write let x in U. And they have the same meaning. So if you see a sentence that says let x in U, it really means the first one. Let x be an arbitrary but now fixed element in a universe U, and this is to correspond with the unified universal quantifier for all x. Okay, so let me highlight that, because I quite often just write let x in U. And then you can just say, not say, but you have to actually find a way to show, for this particular x, show px is true. Of course, this is where all the hard work is done. Show px is true. But that's just the general format. The nice thing about doing so is, because typically you have some description about the set U. Okay, the set U usually is defined as a set with certain properties. So when you say, oh, let x in U, then you can immediately say, by the definition of U, x satisfies that property, and then keep on going. Right. So this is the format of writing direct proof for universally quantified statement. Okay, and then you have the last format, there exist. There exists x such as px. How do you write the proof for that? Well, if it is direct proof, you have to give that particular x. So this is where things gets a little bit confusing, especially for beginners. Because quite often when you see proofs in a textbook of existential statement, it just begins with the definition of x. Begin with how x is chosen. How x is chosen. Begin with define x or pick x to be blah blah blah. Define it in an unambiguous way. An unambiguous way doesn't mean unique. Okay, it doesn't mean unique. You have to at least have some sort of confirmation that your choice of x is actually attainable. Begin with pick / define x to be such and such and such. So you have to give the reader how exactly is x chosen? You must find an element x. Okay, find an element x in U to be such and such and such. And now demonstrate Px is actually true. Show Px is actually true. This is the proof of the existential statement. I mean, do it directly. Of course, this raises a question: how on earth am I supposed to know how to pick x? This takes scratch work. So at the end of this stream, I'm going to give the definition of limit and do a simple proof of limit in calculus. Okay, and of course, perhaps this is, as a first proof, introduction to proof course, the definition of limit is often argued to be a little bit difficult. But I think, I mean, we don't always want to do simple examples and get bored about it. I just wanted to see, okay, what kind of mathematical machinery can we develop just using these tools? And of course, we'll come back to more elementary steps. Okay, so there's a classic example for quantifier is the definition of limit. So let's go. So first of all, we like to motivate the definition. We just don't want to give the sentences and push the axiom. So first of all, let's think about how do you define the limit. Define limit of a function. The classic epsilon delta definition. How is that done? Okay, so this is our diagram. A function f, you can think of as a curve. It doesn't have to be continuous or anything, it's just a function. So, right, this is a point A. We wish to say something like the limit of the function f of x as x approaches A is L. So what is the intuition of this? What is the intuition of this? Well, in introductory calculus course, non-proof based calculus course, you often say something like this. When x gets closer and closer to A, f of x gets really, really close to L. Of course, there's nothing wrong with that. But let's think about an extreme situation. Let's say if the function is just a constant function, let's say L equals L, everywhere. And this is A. If the function is a constant function L, then x don't need to be close to A for f of x to be close to L. Right? So saying if x gets really, really close to A, f of x gets really, really close to L is a little bit misleading. Because what we really care about is f of x close to L, not x close to A. What we really care about is the distance between f of x and L to be arbitrarily small as we want, provided x and A is close enough. So imagine if you have a very steep function, then x needs to be really, really close to A. Because the function is very steep, if x simply deviates from A a little bit, there's going to be a big difference between fa and L. And if the function is really, really flat, then x don't have to be super, super close to A, so that f of x is within your error tolerance. So what we really want is not x to be super, super close to A. What we really want is f of x to be super close to L. We just need x to be close enough to A for that to happen. That's already enough. So that's the intuition of this definition of epsilon delta. It's all about error control. The idea is really idea of error control. And the idea of error control is everywhere in engineering. Because in engineering and science, you almost always never get the exact solution. Right? But you always just want your solution to be good enough. And that's, philosophically speaking, the same as the epsilon delta definition in pure mathematics. So let's write down that definition, okay? And see if there's anything else that needs to be ironed out. Okay, so we say that the limit of f of x Okay, you know what? I will just first use the fully verbal description. We say that the limit of f of x is L as x approaches a, is if the following if for every epsilon greater than 0, epsilon is the error tolerance level. So you want f of x to be within L plus or minus epsilon. This is your error tolerance level. L plus epsilon and L minus epsilon. So for epsilon greater than 0, there exists a delta greater than 0. Delta controls the closeness between x and a. Okay? Remember, we don't need for all delta greater than 0. We don't want the closeness of x and a to be arbitrarily small. We don't need that. We just need x and a to be close enough. There exists a delta greater than 0 such that for every x, if x minus a absolute value is less than delta, then we have f of x minus L to be less than epsilon. Okay, this is incomplete. This is an incomplete definition. Before you scream in chat, okay, I purposely say this is incomplete. We want to add an extra condition here. We want x to be also not a. So imagine, let's say this is actual graph of f, and f of a is this point. F of a is not L. But it should not matter, because as x approaches a, f of x still approaches L, even though f of a itself is not L. So the moral of the story is the limit of a function has nothing to do with the function value at a particular point. So in this definition, it's important to stress, while x and a is close, they're not the same. So we need to add x not equal a into the assumption. So efficient way to do that is simply say the distance between x and a is positive. This way you exclude x equals a. So that's the full definition of f of x equals L. And perhaps it is also necessary to say something about the point A, right? To say something about the point A. So point A, if we want it to be fully rigorous, we need to specify that A is a quote-unquote limit point of the domain of the function. So the full definition would start from, say, f is a function from A to R. Once again, we're getting ahead of ourselves because these notions aren't, functions aren't fully defined, right? Because according to our schedule, function only appears like here. Okay, so we're already jumping ahead. But basically, I think everybody already seen function in some form in high school, in calculus. So I think it's fair for me to write that. Okay, f from the set A to R, where A is the domain of f, and little a is so-called a limit or a accumulation point, and A is an accumulation point or a limit point or limit point, aka limit point of big A. So the idea of accumulation point of a set is that if A is accumulation point of big A, then elements in A can get arbitrarily close to A. Here, because as we said, x approaches A, what guarantees this can happen, right? It can only happen if little a is an accumulation point of A. So, but now we're not going to dwell on this detail, okay? Just because it's a topological issue here. If f is from A to R and A is accumulation point of big A, we say that the limit of f of x is L as x approaches A if the following statement hold. So that's the definition of a limit. As you can see, it's quite involved, right? It involves mixed quantifier. to do this kind of proofs, right, to do this kind of proof, you would actually give the definition of delta. Right? So but before we do this proof, let me know what? Let me give an example. Not a full example. We'll continue this another time because now is already getting a bit late and I need to eat. Example, let f of x to be 4x minus 3 if x is not 2, and if x equals 2, it will just be 1. So let's draw a picture for that. 4x minus 3 is a straight line. Slope is 3, like this. Okay. When x equals 2, if you plug in x equals 2 into the first expression, you get 5. But here we have a discontinuity. So this is not drawn up to scale. Okay, just the idea of the graph. So at 2, the function approaches phi, right, which is fairly intuitive. The actual value is defined as 1, which is irrelevant. Okay, the limit of a function does not care about the function value. Does not care. So we wish to prove the limit as x approaches 2, f of x is 5. Well, how do we proceed before you actually have the full proof ready? So let's say if this is the goal and you know the definition of limit, okay, and write, and we write, by the way, of course this is familiar notation, limit of x approaches a, f of x equals L. So to do this proof, first of all, you need to know the definition of limit, because otherwise there is no logical structure to speak about. To prove a statement, you first need to know the logical structure of the statement. Here, the idea of the definition is error control and is now completely formulated in mathematical language. Implication and sets and all of that stuff. Okay, so there you go. That's our definition. So to verify this, using our template above. So we got all the ingredients needed. See, for all there exist, imply. How do we do that? Right? Just based on our format, you can already stitch together a fundamental, just a template for the proof. You can fill out the details later. What are you going to eat? Cultural curiosity. Good question. I haven't figured it out yet. I feel like it's instructive to go through the step of analysis of a limit proof that happens before you actually write down. Yes, exactly. This is a structure. This is a structure because often you see an analysis textbook is the finished product, right? Because right now we don't even know how to actually crunch out the numbers, but still, simply by staring at the logical structure of the statement, there's already something you can do. And quite a bit, actually. Start with a proof. So, well, because of the universal quantifier let epsilon greater than 0, you need let epsilon greater than 0. As mentioned, what this really says is let epsilon be an arbitrary but now fixed positive number. So to save some writing, let's write let epsilon greater than 0. So this corresponds to the, let me put it on the side, this is for the quantifier, for all epsilon greater than 0. And now you need to demonstrate the existence of delta. So to do that, we say pick or define delta to be what? And in case it is not immediately obvious that your delta is well defined, you have to justify it. So pick or define delta to be what? Okay, the first sentence is already a complete sentence. There's nothing needs to be done to the first sentence. So for the second sentence, obviously, now we still don't know what delta would work. So you can put like a fill in the blank symbol here. Pick delta to be what? This corresponds to the existential quantifier, there exists delta greater than 0. Okay? And then you have another quantifier for all x. So in this case, you can say just let x be arbitrary. Let x be arbitrary, and this corresponds to for all x. Okay. For all x. Okay, and then you have this implication. So what we do with implication, you start by assume the assumption. Assume you have x minus what? What is a here? A is 2. So assume x minus 2 absolute value is less than delta greater than 0. And of course, you need to fill out the actual steps that shows the final inequality which we care about. Actually, what do we care about? We need f of x minus the proposed limit, which is 5, to be less than epsilon. You need f of x minus L absolute value to be less than epsilon. Okay, so this part corresponds to, is for P implies Q, or just say 0, the implication part, okay, the x minus a absolute value greater than 0 less than delta implies f of x minus L less than epsilon. There you go. And finally, you can write the conclusion and say, therefore, by the definition of limit, the limit of f of x as x approaches a is L, QED. So now it's just a matter of finding delta and fill out the actual steps here. To get an idea of how to define delta, you need to do what we call a scratch work. So in a scratch work, it is okay to assume the conclusion. Sounds absurd, but this is how proofs are actually written. You first start by assuming your kitty is doing, I love your, thank you very much. Thank you very much. So I was like, you first by assuming, you start your scratch work by assuming your conclusion is true, and you try to reach your assumption and make sure every step of the way the logic is quote unquote reversible. Okay, so let's think about how this is done. So here, this is our scratch work. We need to explore what delta needs to be. Okay, find delta. F of x minus L, absolute value less than epsilon. What does that mean? It means f of x, well here, x is not 2, so you use the first expression, 4x minus 3 is f of x. What is L? That's 5, absolute value less than delta, greater than 0. Actually, no, you don't have greater than 0 here. So this is what it means. And now do some algebra, you get 4x minus 8, absolute value less than epsilon. So you can take out the 4, you get x minus 2, absolute value less than epsilon over 4. And it's very similar to what we wanted, right? So we wanted, so actually, not what we wanted, this is what we wanted, but we assume x minus 2 absolute value to be greater than 0, and less than delta. So it is clear that you should pick delta to be no more than epsilon over 4. So there you go. You have your choice of delta. So you can just write, fill in the blank here. This is, we use a different color. It's because it's the actual set of the proof, so we use blue, okay? These aren't necessary part of the proof. Okay, so now we have delta chosen is just a matter of verifying this option work. Okay, so anyway, let's begin. Okay, assume this is true, then x minus 2 absolute value is less than, here what we have, epsilon over 4. Multiply 4 on both sides, get 4x minus 8, absolute value less than epsilon. And then you can write 4x minus 3 minus 5, absolute value less than epsilon, i.e. f of x minus 5, f of x minus 5 is less than epsilon when x is not, x is not 2, right? Because 4x minus 3 is f of x when x is not 2. And finally, conclude the proof. The limit of f of x is 5. So that's the complete proof. But if you never did the scratch work and you read the actual solution or the proof in the real analysis text, you would have a great reaction. You will have a great reaction. Okay, look at this delta. I don't know how to pick the delta. I guess I'm just not a math person, as they say, right? And as you can see, there's really no mystery to it. Right? You start by laying out the logical structure according to the statement. And sometimes in textbooks, the definition is not written in a symbolic format. It's verbal, but it doesn't matter. You can always convert it to logical statement with quantifiers and all of that. Actually, I would like to just give a concrete example, okay? And there's no desire to explain things in detail, but basically, here, let me just pull out Axler, okay? The Axler's text on measure theory. To see how basic techniques like this one is really the backbone of advanced mathematics. So here, just a statement. I'm not going to go into the detail because this is not a measure theory stream. If you're interested, follow the measure theory stream. We might do another one this week because I want to make more progress in this, because I feel like there are certain tricks I have not yet mastered. I want to get up to speed. So anyway, doesn't matter. Coming back to a particular example. So just give me your gut reaction when you first read this. Okay, the theorem here is as 2.48, limits of an S measurable function. Okay, so assuming you have a measurable space and a sequence of measurable function, assuming the sequence converges to a function, say f of x, everywhere in big X, then prove the limit function f is a S measurable function. Okay, so just as a high-level description, the whole proof hinges on this identity, hinges on this set identity, 2.49. And the rest is just verifying this identity. After you verify this identity, the proof is trivial. Okay, so this whole proof hinges on this identity, but where on earth does this come from? Right, so like when I first did the stream, I think it was last Thursday night, I was trying to come up with a justification, not a justification, but a motivation for picking this choice. I was able to verify what follows. It is indeed a true equality. But I was just thinking, how on earth am I supposed to come up with this construction when I do this proof on my own? Right? And this is a common frustration in analysis. I think when that happens, typically is because the author did the scratch work elsewhere and only presented the finished proof, because that's the standard of mathematical publishing. Okay? But for a beginner, for people who try to learn this stuff, I mean, even when you can mechanically verify this identity, let's say, if you don't know the scratch work, it is still difficult for you to understand what is really going on. Even though mechanically, okay, all the steps can be verified, it is still unclear what on earth is happening. So actually yesterday, thankfully, I came up with the appropriate scratch work. So here, yeah, I did the exploration, and it turns out that it is nothing but a manipulation of quantifiers. You just unpack the definition of limit into quantifiers like we did earlier, and express that into set notation. The relationship between quantifiers and set notations will be covered in future. So basically, there's no mystery whatsoever. It is just a manipulation of quantifiers. And that's exactly what we did earlier. So sometimes statements aren't written explicitly in terms of quantifier, but they can be unpacked into them. So here, yeah. Here we've written the definition of limit using quantifiers. Sometimes it's described verbally. It does not matter. You should be able to translate between them freely. And after that's done, you can actually, a lot of the progress are actually automatic. Okay, so hopefully this demystifies some of the sort of the mystery surrounding proofs, especially in analysis. And thank you very much for watching, and I'll see you guys next time. Bye.